since we hit 50 participants, should we take that as a cue to start? All right. So welcome everyone to this workshop, which we're calling Algorithms with Predictions. So to give, I want to start with just a little bit of an overview, maybe by example, of what this area is about. And we have 4 exciting talks delving into different parts of this recent kind of line of work. So maybe the easiest way to go at it is just by example, right? If we go back and slowly wake up and say, what is Algorithms 101? I give you a sorted array and a query, and I just want to see if an element is in the array. What do we do? Well, we're just going to run binary search, right? So you're going to look in the middle of the sorted array, decide whether you should recurse to the left or to the right, and keep on going, right? And we all know that this takes logarithmic time, logarithmic in the length of the array overall, right? So how can we make this better? And there's a question that says, well, suppose you had a predictor that kind of knew something about the quantile distribution in this array and said, well, if I'm looking for a query Q, where should this Q appear? And the predictor doesn't need to be very good. We just know that 7 is kind of a small number for the arrays that we expect them to see. So instead of starting in the middle, I'm going to start a little bit further to the left. And this is where the prediction tells me where to start. And then what do? Then I do the same thing as I did before, right? And I can, instead of doing just a binary splitting, I'm going to do a doubling binary search, right? So I'm going to look 1 away, it's to the left. I'm going to look 2 away, I'm going to look 4, and I can do a binary search there to say, where is this number that's appearing, right? So this is something that we can do. This is something where we can train a predictor because maybe we're doing this search every single day over similar data sets. And the key here is that if we write if we call it by eta 1 the error that we have in our prediction, right? Like, which is the difference between the cell that we started with and the cell where the element actually appeared or should appear, then it's easy to convince yourself that the running time now with this prediction is just logarithmic in the error that we have, right? And so as long as the error is sublinear, really, we, at least in theory, should see a gain in the running time. And empirically, this was the leading work by Tim Kroska et al. That say you can actually do this. You can actually train such a predictor, and you can see performance wins, right? So you can speed up binary search if you're doing it on similar data day after day, right? So there are 2 kind of nice things in this very simple example. If your predictions are good, you actually recover constant lookup times. If your predictions are bad, you don't lose much or almost anything by using the prediction. So you lose a constant factor here, but asymptotically, you're not actually losing anything, right? And so you get this kind of best of both worlds scenario where you've tied the performance of the algorithm that you have, in this case, the running time, to the quality of the prediction. And you sort of reduced it to machine learning to some extent, right? And there's a number of reasons why this is interesting. One way I like to view it is that it's another way of going beyond worst case analysis, right? So if we want to understand or subvert some of the lower bounds that we have, how can we do it? Well, traditionally, we've looked at stochastic assumptions, right? Items are drawn from distribution. Maybe it's random arrival in kind of secretary problem kind of settings. There's been some interesting work on optimistic analysis that say, well, I think it's going to come from this distribution, but I want to control for the worst case as well. But what do all of these have in common? All of these give you some foothold into predictability of the input. It tells you that the input is not arbitrary, right? But is likely to have some particular property. And how do you take advantage of that property is the key to the analysis that you're doing, right? And so the question that we ask here is it enough to know the performance of the predictor? And if you know the performance, is that enough of a foothold to then say, oh, here's something that we can do better. We can get better competitive ratios, better running times, better space complexity, and so on. Right? And so there's kind of 3 different thrusts in this area of algorithms with predictions. One, and we'll hear about all of these today. One is kind of understanding what predictions are good. Right? What predictions can we actually make? What predictions generalize? What predictions have low sample complexity? Another one is to say, well, how would we use them effectively? Right? If I give you a prediction, how do you actually use it? It was trivial to use it in the binary search example, but as we'll see, like there's more complicated ways of using it. And the third one is really understanding when are these predictions not enough, right? And where is it that even with some amount of prediction, you can't get beyond the upper bounds, let's say, that we have without any predictions at all. So this is the schedule for the rest of the afternoon. We're going to start, where are we on time? We're a little bit early, but that's okay. So we'll start with a talk by Tim on data-driven algorithm design, which really predates some of this work and really delves into the complexity questions of how do you, given a lot of data, a lot of repeated applications, how do you get good algorithms out of it? And then we'll go on from there. Tim, do you want to go jump in?
See the slides okay? Yeah, okay. Okay, thanks very much, Sergey. I also wanted to thank the other organizers, Pyotr, Yaron, and Ali, for putting together this workshop. I'm very excited to participate and very excited to see the talks of the other speakers as well. So as Sergey said, the work I'm going to be talking about, it's a few years old now, but still, I think, connected to the themes of this workshop, something we're now calling data-driven algorithm design. And this was all work I did joint with a former PhD student of mine, Rishi Gupta. So this topic is one of many, many facets of an area that, as Sergey said, some of us like to call beyond worst case analysis. So I hope you'll forgive me if I spend a minute promoting the fact that there's a new book coming out on exactly that topic. The book is pretty much done. We're just waiting for Cambridge University Press to kind of finish the production. And it's a sprawling topic beyond worst case analysis, and accordingly, it's sort of a sprawling book. So there's 30 chapters, 40 authors who you see here, including Sergey, for example, and Michael Mitzenmacher, one of the other speakers today. Really leading world experts in algorithms, talking about the many different facets of this area. I just wanted to flash quickly a list of the 30 chapters, all a wide array of topics, but I think they're all super cool topics where there's opportunities for lots more research. Everything from trying to explain why simple hash functions work, to the classic models of smooth analysis, to ways of getting around NP hardness for combinatorial optimization problems, to many new connections between theory CS and machine learning and statistics. And last but not least, actually the very last two chapters in the book, in italics here on the bottom, those are both very closely related to this workshop. So chapter 29, that's by Nina Balkin. And so that's on exactly the same topic I'm going to be discussing. I'm talking about sort of the first work in that direction. And then Nina and many other researchers have really developed that into a very powerful, coherent theory. If you want to learn more about that, I think her book chapter, Data-Driven Algorithm Design, is a great place to start. And then the last chapter, Algorithms with Predictions, right, same name as the workshop, that's by Sergey and Michael Mitzenmacher, one of the speakers later today. And I think that's another great entry point into this very exciting literature. All right, so forgive me for the quick promo. Let's get into data-driven algorithm design. So I'm an algorithms person, like many of you. I think about algorithms pretty much every day. And when people know you're an algorithms person, something that starts happening is, someone will walk into my office, right? So maybe a colleague, maybe a student, they'll sit down in the chair, and they'll say, Tim, you're an algorithms person. So, this problem came up in my work, right? And the problem could be anything, but let's, say it's like the TSP. And they say, so, as an algorithms person, give me some advice, give me some guidance. Which algorithm should I use to solve my problem? And it's a very innocuous sounding question, right? And it's not the sort of thing you would like to ask an algorithms person, but right, it's a really tricky question to answer, actually. And it's sort of tricky in the same way that, like, if you had just met a medical doctor at a party, if you went up to them and said, hey, doc, I've had this stomach ache the last couple of days, what do you think I should do? And the reason both these questions are sort of tricky in the same way is that the correct answer depends on additional details which have not been divulged, right? So just as there could be different causes for a stomach ache, each demanding their own specialized medicinal treatment, so might different applications involving the TSP generate different families of instances, each benefiting from their own specialized algorithmic treatment, So just as the doctor, might tell you to sort of, take some Pepto-Bismol and call me in the morning if you're not feeling better, I might tell the person in my office, well, try local search and call me in the morning if you're not happy with the results. So the point of the story is just that, especially once you get to sort of NP-hard problems and that kind of thing, the sad fact is there's no silver bullet algorithm, which is just always the right one to use. Really, the right algorithm to use for the problem actually depends on the application, specifically on the instances of interest. So I want to start the talk just with 3 quick examples that I think are kind of fun in their own right, but I'll also sort of give you a sense of, when we were developing this theory, what is it we wanted to capture with the theory that we were developing. And again, all of these will sort of reinforce this point about the best algorithm for the job, depending on the application. So here's a graph I pulled from a paper by Smith Miles et al. A few years ago, although, as you can imagine, there's similar graphs lots of other places in the literature on empirical approaches to NP-hard problems. So what's this paper about? Well, they did something conceptually pretty straightforward. They thought about the NP-hard graph coloring problem, and they scoured the literature, right, for the 7 sort of leading best kind of heuristics for graph coloring. Those correspond to the 7 different colors that you see. And then they also sort of collected what were all of the standard hard benchmarks that people cared about. And then they ran each of the 7 heuristic algorithms on each of those graph coloring instances. And they just wanted to see which of the 7 did the best. So what you see on this plot is each dot on this plot corresponds to one of the benchmarks, an instance of graph coloring. And the color of that dot indicates which of the 7 algorithms performed the best on that particular graph coloring instance. And the main thing I want you to take away from this slide is just that, sort of each of the algorithms has its own sort of region of dominance, right? So none of them are across the board the right one to use, but there are instances where each of the algorithms does well. So sort of the implicit advice that this paper is giving you is, if you have to solve graph coloring, figure out where your instance sort of falls on this plot, and then, use the algorithm that corresponds to, the color that region is. So a second example concerns satisfiability. So as you may or may not know, every year or every other year, all the sort of SAT nerds from across the world gather together and have Olympic-style SAT competitions. So people bring their latest and greatest SAT solvers, people bring their sort of hardest, most interesting benchmark instances and hard instances of satisfiability, and they sort of run all the SAT solvers on all the instances that people brought. So they have a competition, they give out medals, and so on. This has been going on for at least a couple of decades. And a little over 10 years ago, there was a team out of University of British Columbia. I think this was for the 2007 SAT competition that's happened. And they were, they're talking amongst themselves and said, it'd be really fun and cool to enter one of these SAT competitions. And the only problem is that the deadline was 2 weeks away. And so they really had neither the time nor the inclination to kind of, from scratch, develop some sort of novel SAT solver to submit in the competition. So they had a sort of cheeky idea instead. So what they did is they observed that all of the, they looked at a bunch of the kind of latest and greatest SAT solvers, so like winners of the 2005 competition, which were mostly open source. And they observed that, something very similar to what we saw on the plot on the last slide. They observed tremendous heterogeneity in performance of the sort of cutting edge SAT solvers. And I really mean that in 2 senses. So first, if you fix the solver and vary over SAT instances, you get orders of magnitude differences, many orders of magnitude differences in running time for different instances. But maybe more interestingly, if you fix the instance and then range over SAT solvers, you would also see orders of magnitude variation in the running times of the solvers on that instance. So just like on the last slide, the different algorithms seem to have their own sort of regions of superiority. So the UBC team, what they submitted was really kind of a meta algorithm or an algorithm portfolio where literally it just made use of 7 SAT algorithms, and on the fly, when it had to solve an instance, it figured out which of the 7 SAT algorithms which of the SAT solvers it wanted to use. And it did it in a way which conceptually is pretty straightforward. So you just associate with every SAT instance a feature vector. Some of those features are obvious, like clause variable ratio, or the size. Others are not so obvious, right? So they used Knuth's search tree estimate of the solution space size. They also just used the sort of performance of unit propagation in sort of, roughly a second or something like that. In any case, for every SAT instance, they associated a feature vector. Then using benchmark instances, they learned 7 statistical models. one for each of these SAT algorithms. And the model the goal was to predict the running time of that particular SAT solver as a function of the feature vector of the satisfiability instance. So they learned these 7 statistical models predicting running times of different solvers, and then they used it in sort of the most straightforward way imaginable. So when their SAT solver, SATzilla, had to solve a SAT instance in the competition, it just computed the features of the instance, evaluated each of the 7 sort of predictors to get predicted running times for the 7 SAT solvers, and then they ran the one with the smallest predicted running time. And they completely cleaned up. They got lots of medals across the different competitions. They repeated the feat in 2009, and so now it's actually to the point that these portfolio-based solvers are actually banned from most of the competitions in these SAT competitions. So that's a way to exploit the fact that sort of different algorithms do better on different types of instances. Last example I want to mention concerns parameter tuning. So we're hearing about that a lot these days, like last 10 years or so, due to the rise of machine learning, where it sometimes goes by the fancier name hyperparameter optimization. So what's funny is, we think of something like gradient descent, simple as it is, we think of it as an algorithm, but it's really kind of underspecified, actually, right? So gradient descent becomes a concrete algorithm that you can run only once you instantiate several parameters, right? So maybe most notably, like the step size you're going to use in gradient descent. Or for another example, if you're using ridge regression, that's not really an algorithm, that's a family of algorithms, which is parameterized by the coefficient of the L2 regularization term. So that's just one place where you, in effect, have to really choose from, one instantiation of what's kind of a meta algorithm with possibly many parameters. I do want to mention, it's not like this problem didn't exist before machine learning. This has sort of always been, part and parcel with algorithm design. So just to give you one example, like if you take one of the leading linear programming solvers, Cplex, that's we think of the simplex method, or we think of Cplex as like an algorithm, but again, it's really a highly parameterized kind of meta algorithm. In fact, there's 135 parameters, so many that Cplex gives you a 221-page reference manual explaining what they're for. Now, with 221 pages, you might be hoping for some sage advice, some guidance about how to set those parameters, depending on what your application looks like. But you'd be out of luck. The manual really doesn't say anything other than you may need to experiment in this 135-dimensional space. So thanks a lot, Cplex. All right, so all of these are just to point out that, all around us, really, there is this problem of selecting one algorithm from among many, right? So sometimes those algorithms could look very different from each other, like the 7 SAT solvers. Sometimes they could all be different instantiations of one meta algorithm, like in the machine learning examples. In any case, these were the kinds of examples that were like rattling around in our brains when we set forth to kind of do some theory. So we really said, what would a theory look like that kind of mimics what's happening in these application domains? And we asked that question, the first thing you realize is that whatever it's going to look like, it's not going to look like worst case analysis, okay? Because the whole point of worst case analysis is to be agnostic to your instances, right? To have no data model. Or, if there is a data model in worst case analysis, it's what I like to call the Murphy's Law data model. So whatever can go wrong will go wrong. In other words, the instance you have to solve is actually an adversarial function of the algorithm that you choose to use. So that's not the theory that's going to make sense for these applications. The good news is we can stay solidly within the comfort zone of theoretical computer science. We don't have to look that far. And in particular, we're going to draw on learning theory, specifically statistical learning theory, to think about this problem. So what's the correspondence between sort of the standard learning theory questions and algorithm selection, algorithm design? Well, in learning, right, the key ingredient is a class of concepts, or maybe it's called a class of hypotheses. What do we care about? We care about algorithms. Okay, so for us, we're not going to have a class of hypotheses. We're going to have a class of algorithms from which we want to pick one. In learning theory, you assess how good a particular choice of a hypothesis is using a loss function. So we're just going to use some notion of algorithm performance as the loss function that we want to optimize. And then what I'm going to show you today is, hopefully if I have time, both models that are just very standard models in learning theory. First of all, kind of a pack learning type model, and then second of all, an adversarial online learning sort of regret minimization setup. So that's where we're going. On this slide, I want to make this correspondence a little more precise, right? So it's selecting an algorithm from a class and sort of standard sort of learning theory formalism. So we have some fixed problem pi we want to solve. Maybe it's SAT, maybe it's graph coloring, whatever. We have some family capital C of algorithms that we're willing to use. For this slide, if you want, think of capital C as finite, like those 7 graph coloring heuristic algorithms or those 7 SAT solvers. It really gets interesting when C is infinite. And I'll show you on the next slide a simple example of how infinite classes of algorithms arise through parameterization. All right, so we've committed to this class of algorithms that we're willing to use up front. Okay. Notice this already looks quite a bit different than sort of traditional sort of TCS approaches to algorithm design, where you start with a problem and you're willing to just throw the kitchen sink to get whatever you can and say polynomial time or something like that. Here we're really thinking someone has pre-committed to what algorithm they want to use. Like they know they want to use Cplex, they're just not sure about the parameters. They know they want to use gradient descent, they're just not sure about the step size, and so on. That's the kind of application we're thinking of. So in addition to the algorithms you're willing to use, capital C, we need a notion of algorithm performance. And so the theory we're going to discuss is going to be totally agnostic, really, to what notion of algorithm performance you use. Could be running time, solution quality, approximation ratio, whatever. I am going to assume that it's bounded. And so by scaling, we're just going to assume that this cost function is bounded between 0 and 1. And now what we're going to want to do to get the correspondence with learning questions is we want to associate with each algorithm in our class a real valued function, okay? The domain of that function is going to be all possible instances of the problem pi, so like all possible instances of satisfiability. And the range of that function, okay, it's real valued, so the output is just going to be the performance of the fixed algorithm A on that input. In other words, we associate each algorithm with a real function, which is its performance profile. Think of it as like a big vector indexed by all possible instances you might run that algorithm on. Okay, so for each algorithm, we can associate a real valued function corresponding to its performance on all instances. All right, so I promised you a sort of natural class, infinite class of algorithms you might want to think about, not just 7. So let's look at a famous NP-hard problem, weighted independent set. So I'll give you an undirected graph. The vertices have non-negative weights. You want to pick the subset of mutually non-adjacent vertices so that their total weight is as high as possible. So for example, in this 5-vertex graph I've shown you in green, the maximum weight independent set, it has weight 8. So independent set, this is an NP-hard problem. It's even NP-hard to approximate to within any interesting factor. So you're going to have to use some kind of heuristic algorithm if you want to tackle independent set problem in a real application. And greedy heuristics are a natural place to look. So like one very simple heuristic would be, you say, well, we want to maximize the weight, so let's do a single pass through the vertices from the maximum weight to the minimum weight, and let's always sort of pick a new vertex as long as we haven't already picked one of its neighbors, as long as it wouldn't destroy feasibility. Okay, so for example, in this graph, you would first pick the weight 4 vertex, that would block the 3 weight 3 vertices, and then you'd be stuck picking the weight 2 vertex at the end. So there you get the independent set of the 4 and the 2 for a total weight of 6. Another heuristic for independent set that many people have looked at is to normalize by the degree. So basically sort vertices by their bang per buck rather than by just their weights. Okay, so the numerator of the ratio is indeed the benefit of selecting that vertex, its weight. But in the denominator, you scale, recognizing that by choosing the vertex V, you're knocking V out of further consideration along with all its neighbors. So the weight divided by 1 plus the degree. Those are probably the 2 most commonly studied greedy algorithms for the simple greedy algorithms for weighted independent set problem. But it's, if you wanted to, you could interpolate between the 2, right? There's no reason to do this for like a worst case approximation guarantee. But in a real application, for all you know, taking the square root of 1 plus the degree is going to be better than either of the 2 heuristics we started with. And so just by this simple interpolation, just saying, you know what, I'm going to use an exponent in the denominator, which is some real number between 0 and 1. Now we really have one separate algorithm for each possible choice of the exponent p. So this is really an uncountably large family of algorithms. Clearly it's sort of well structured, but it really is not a finite class of algorithms. Okay, so let me now be precise about the first model. First model is our offline model or batch learning. So those of you who have seen sort of pack models, this is going to be exactly the same thing. So the 2 things we know up front, we know what the problem pi is, and we know what class capital C of algorithms we're willing to use. Something we don't know is we don't really know what are the instances relevant to our application, okay? And the way we're going to model sort of what's special about the application, we're just going to model it through a probability distribution, capital F, over the possible instances of the problem pi. Okay, so that is how we capture this idea of the instances relevant to the application. We capture it through this probability distribution, capital F, over inputs. Okay, we do not know capital F a priori, except in as much as we may have gotten our hands on some representative benchmark instances. Mathematically, that means we have some number of IID samples drawn from this instance distribution capital F. Okay, so we're going to have S samples, where S is a parameter we're going to be very interested in, S samples from capital F. Obviously, the more samples we have, the better. In some sense, we approximately know what the instance distribution looks like. The goal then of a learning algorithm is you want to sort of, recommend an algorithm. You want to sort of, based on the knowledge you have about the application, meaning these S samples from this unknown distribution, you want to make a recommendation. So you want to choose an algorithm from the allowable class capital C that minimizes or sort of optimizes the expected algorithm performance, where the expectation is over this distribution capital F that you do not know. Okay? So that is ideally what your learning algorithm would do. So just based on a finite number of samples, it outputs an algorithm, maybe not the optimal one, but at least almost the optimal one for the true unknown distribution, capital F. Okay. Let me briefly say there's sort of a precursor model of self-improving algorithms, which is somewhat related. There's also going to be a chapter by C. Shashadri on self-improving algorithms in the Beyond Worst Case Analysis book, so that's something you can check out. The goals tend to be different. In self-improving algorithms, the focus is more on sort of the space complexity usually of the learning algorithm, whereas we're going to be squarely focused on the statistical questions, on the sample complexity. In other words, we're really going to focus on how big does S need to be, how many benchmark instances do you need before you can, with high confidence, make a good recommendation about what algorithm you should use for that application domain. All right, so this is really a statistical learning theory question, sample complexity, and so it's natural to lean on the statistical learning theory toolbox. And the main tool we're going to use, so maybe I should say, like, what's the kind of meta plan? What are we hoping we might be able to prove? Well, for sample complexity, kind of the first lesson you get out of learning theory is ways to quantify the idea that simple things are easy to learn. You can learn simple things from not many examples, whereas complex things can take a lot of data to learn. So we'd like something analogous for algorithms. Like if you're just trying to recommend a good algorithm from a relatively restricted class, you need a quite small number of benchmark instances to make a good recommendation. Whereas if your family of algorithms is very complex, maybe you need a lot of data to make a good decision. So to make that precise, right, we need to have some notion of what does it mean for a family of algorithms to be simple or to be complex. But these kinds of questions are exactly in the wheelhouse of learning theory, right? What they're really good at is having functions that characterize in interesting ways the complexity of a family of functions, right? Now, we're not interested in functions per se, we're interested in algorithms. But remember what I said, to each algorithm, we can associate a real valued function, which maps instances of the problem to the performance of the algorithm on that problem. So when I talk about the pseudodimension of a family of algorithms, I really mean the pseudodimension of the family of functions corresponding to those algorithms. So let me say a little bit about pseudodimension. So on this slide, I want to I'm going to be addressing those of you who have seen VC dimension before, basically just to convince you that this is exactly the same thing. For those of you that haven't seen VC dimension before, I wouldn't really worry about this slide. I would maybe just sort of, put it on your future to-do list. It might be a cool concept to learn about. It's very important in machine learning theory. All right, so VC dimension, that's a complexity measure for families of 0, 1 valued functions, so families of binary functions. Now, our functions, the running time or other performance characteristic of algorithms, they're not binary, they're real valued. So the pseudodimension is basically the obvious extension of the VC dimension to real valued functions, okay? One way you could think about it is, right, so how can you turn a real valued function into a binary function? Well, you can just threshold it. And actually the pseudodimension, one way to define it is it's actually the largest VC dimension you can get by turning your real valued functions into binary functions by thresholding. Okay, so it's really just kind of exactly the same thing. So just like the VC dimension, if your function class is finite, then your pseudodimension is also finite. In fact, it's even logarithmic in the size of your function class. And also, just like, so the interesting case technically is really when capital C is infinite. But as we've seen in this algorithm selection problem, there are natural cases where C is infinite. And just like the VC dimension, what it means to have a big dimension, so like pseudodimension at least D, it means your function class has to be pretty crazy. It means it has to exhibit an X. So not only does your function class have to have 2 to the D different functions in it, but it actually has to exhibit 2 to the D fundamentally different behaviors on a fixed size D sample. Okay? And again, for those of you that have seen VC dimension, this will be familiar. This is the notion of shattering. For those of you that haven't, I wouldn't worry about it. You won't need this except in a short proof in a couple slides, okay? So that's the definition of the pseudodimension. Why do we care? The reason we care is because the pseudodimension governs the answer to the sample complexity questions that we're interested in. Remember, we want to know, for a given family of algorithms, how many benchmark instances do we need before we can, with high confidence, make a good decision? That's the sample complexity question. And the answer is going to be exactly the pseudodimension of the family of algorithms, okay? So here's kind of the classic result about pseudodimension, again, so 20th century stuff, classic, which says that, you know, if your family of functions has low pseudodimension, then the learning problem also has low sample complexity, okay? So specifically, if your pseudodimension is D, right, so for us, again, we're talking about the pseudodimension of the real valued functions associated with the algorithm class. So if the number of samples is at least D over epsilon squared times log factors, then in fact you can, with high probability, return an algorithm. Okay, it might not be the optimal one for the unknown distribution capital F, but it'll be within epsilon in expected performance of the optimal algorithm in capital C for the unknown input distribution capital F. Moreover, this guarantee holds for the algorithm which is simply the best on the samples, okay? So whichever algorithm has the best average performance over the S benchmark instances that you have, this guarantee actually holds. And so the conclusion generalizes, right? So the expected performance of the algorithm on the true population will be within epsilon of optimal. Okay, so that's why we care about the pseudodimension. We care about it because low pseudodimension is a sufficient condition for low sample complexity, which is exactly what we want. We want to be able to learn good algorithms from minimal data. Now, all this theory would not be very interesting to us unless the families of algorithms that we actually care about happen to have small pseudodimension, right? Otherwise, all of this is irrelevant. So I have to tell you as a quick aside, so back when Rishi and I were kind of first working on this project, like, you know how it is, so how you like sort of bump into your theory friends and they kind of ask you about, you know, what research problem you're working on. So there was a period of time where my answer to that question was, I was working on computing the VC dimension of greedy algorithms. And everybody I told that to looked at me like I had lost my mind. It was clear it just somehow did not type check. These just seemed like sort of two totally different worlds. And maybe one of the takeaways from the talk, you know, especially once we do a sort of short proof, is that not only do these two concepts fit together like chocolate and peanut butter, but actually it's really quite analytically tractable as well to get a handle on the pseudodimension of natural families of algorithms. Okay, so I want to give you a taste of that in the next couple of slides. All right, so we have results that are pretty general, and other researchers, you know, Nina Balkin and collaborators and others have results which are, you know, still quite a bit more general. But, you know, it's a short talk and a workshop. So let me just sort of give you the flavor of the kinds of things we proved, our sample complexity bounds, through an example. And it's going to be the same example that I've been, you know, using as a running example, these weighted independent set greedy algorithms, where you sort the vertices up front by ratio between the weights and 1 plus the degree raised to some exponent, say between 0 and 1. So this is an uncountable class of algorithms, and yet I claim it has a pseudodimension which is finite and small. Specifically, pseudodimension big O of log n. Here, n denotes the largest number of vertices that you're ever going to see in one of the graphs that you have to deal with, okay? So that's the claim. I want to give you a sort of short proof sketch. So what does it mean that you, so this again will be sort of most accessible to those of you that have seen VC dimension at least once in your life. So what it means to prove an upper bound on the pseudodimension, it means that you cannot shatter sets that are bigger than that amount. So to say it has pseudodimension O of log n means you only have a hope of shattering with your function class sample sizes up to O of log n. So in other words, for any bigger sample, we need to show that you do not actually have the requisite exponential number of fundamentally distinct function behaviors. So that's what we're going to show. So again, what is our function class, right? So we have this family of greedy algorithms indexed by P. For each choice of the exponent P, we have a separate algorithm. For that algorithm, we have the corresponding function, mapping the weighted independent set instance to the weight of the independent set output by that heuristic. That is the family of functions we're talking about, and that's the ones where I claim has pseudodimension O of log n. Now, one reason this is non-trivial is because there's really, you do not have the type of Lipschitz properties you might want of this family of functions. In other words, it is not the case that if you sort of perturb the parameter, perturb the exponent P just a little bit, it is not the case that the weights of the independent set returned necessarily changes by only a little bit. So to see that, remember we're using these greedy algorithms, right? So initially they sort of sort all the vertices. And if I make a tiny change to the exponent from p to p prime, that might well reverse the result of one of the comparisons used in the sorting of the vertices. So even the very first vertex considered by the greedy heuristic algorithm might be different for p and p prime super close to each other. And then of course, two greedy algorithms, if they make different decisions in iteration number one, God only knows what happens in the rest of the iterations. They can conclude with utterly different independent sets. Okay, so that's part of the technical challenge here. You perturb p by an arbitrarily small amount, you can get arbitrarily big changes in the weight of the returned independent set. However, here's what we do have going for us. Suppose we fixed a finite sample capital S. Okay, so we fixed like 100 instances of weighted independent set. Once you've fixed a finite number of instances, it is no longer the case that there's genuinely an infinite number of different algorithms. Now there's really only a finite number of equivalence classes of different algorithms with respect to this finite collection of inputs. Let's make that precise. So call two different choices of the exponent p and q, call them equivalent if the corresponding heuristic algorithms run identically on all of the 100 weighted independent set instances in capital S. So in other words, doesn't matter if you use p, doesn't matter if you use q, the vertices wind up getting sorted in exactly the same way. And so then, of course, the output of the algorithm will be the same either way. What I'm going to argue on the next slide is that a lemma, which says there can't be that many equivalence classes. There's only a polynomial in n and s number of equivalence classes. Here, n, again, is the number of vertices, and s is the number of samples we have in capital S. Let's notice that if that lemma is true, then we are done. Okay? Why are we done? So remember, to have a pseudodimension of d or more, you have to exhibit an exponential in d number of fundamentally different function behaviors on a size d sample. Well, within an equivalence class, these algorithms are doing exactly the same thing. Okay, so within an equivalence class, we only get one behavior, and that's it. So if you only have a polynomial number of equivalence classes, and you need an exponential in s number of distinct function behaviors to shatter a set, you have no hope unless the set is only O of log n. Okay, so just a simple counting argument shows that if you happen to have a polynomial number of equivalence classes, you're good to go. Pseudodimension is O of log n. All right, so let's move on to the lemma. And again, this will just be sort of a high-level sketch, but if nothing else, I want you to take away from this slide that, so even if you don't follow it line by line, you should come away with the impression that, like, this isn't that hard, right? So, like, if you wanted to bound the pseudodimension of your own family of algorithms, good chance you could do it. That's sort of what I want you to take away. So what are we trying to prove? So we're looking at the number of equivalence classes. So we have our 100 weighted independent set instances. We have our set capital S of inputs. And we're thinking about varying the exponent. And we're trying to see how many different behaviors do we get? How many equivalence classes do we have? I'm trying to say there's a polynomial number. Well, these greedy heuristic algorithms, once you've sorted the vertices at the beginning, the rest of their behavior is fixed. It just goes sort of in a deterministic way over the ordering that you chose. So in other words, if you have two different choices of the exponent p and q, where all of the relevant comparisons get resolved in the same way, then you're going to wind up using the same sorted ordering of the vertices. You're going to wind up outputting exactly the same thing. So really what we want to understand is, how frequently can comparisons be resolved differently depending on your choice of exponent. So let's zoom into one particular relevant comparison. So of the 100 weighted independent set instances, pick one, number 17, pick two of the vertices of that graph, the 7th vertex and the 23rd vertex. And let's think about the comparison between those two vertices of that instance. So there's two vertices, v and x. Each one has a weight, and each one has a degree, okay? I want you to think about taking the exponent, initially setting it to 0, and then increasing that exponent p toward infinity, okay? Let's see what happens with this comparison. When p equals 0, the winner of the comparison is just whichever of the two vertices, v or x, has higher weights. Okay? That's what happens when p equals 0. Now, as we take p bigger and bigger, if the higher weight vertex also has a higher degree, then eventually p will get so large that the result of this comparison will flip in the opposite direction. Okay, and the other vertex will start winning. The other lower degree vertex will start winning. So that's a flip in the comparison. That's a fundamentally different behavior at that sort of threshold exponent. But the key point is you can keep taking P to be as big as you want. The comparison will never flip back. Once it flips to preferring the low degree vertex, it will continue to prefer the low degree vertex forevermore for all larger values of P. Okay? So for one particular comparison, for one choice of a pair of vertices from one of these instances, over all P's, the result of that comparison flips over only once. Now, we only have S instances. We only have n choose 2 choices for a pair of vertex from a given instance. So that means the number of comparison flips as you go from 0 to infinity over all of the relevant comparisons is only n choose 2 times S, polynomial in n and S. Okay? And again, if all the comparisons come up the same way, then the algorithms output exactly the same independent set. So that's why there's only a polynomial number of equivalence classes. And again, that goes back and implies logarithmic pseudodimension for learning for this family of algorithms, which again, by statistical learning theory, implies a sample complexity bound of logarithmic for learning the best choice of P from representative data. As I said, there's much more general results. I won't have time for it now, but you can check out the paper or you can check out Nina Balkin's chapter in the Beyond Worst Case book. I do just want to say a couple minutes about a second model. I won't say much, but I'll say a little bit. Another super well-studied learning theory model is online learning and regret minimization. So here there's two differences between the offline batch model that we were just discussing. First difference is obvious, it's online. So you don't get all the weighted independent set instances up front. You get them one by one, and each day you have to pick an algorithm to use on that day for whatever sort of instance shows up on that day. The second difference is that it's not stochastic, there's no unknown input distribution. Instead, there's an adversary feeding you, say, an instance of weighted independent set at each time step. So you pick a randomized strategy at the beginning of a time step, the adversary picks an instance, say a weighted independent set based on your randomized strategy, and then one of your algorithms is selected and run on the adversary's input. And you incur whatever cost that algorithm has on the adversary's input. Now, whenever you have this sort of adversarial model, you have to choose the right benchmark. We're just going to use the standard one in online learning, which is just the best fixed option in hindsight. So given the capital T adversarially chosen inputs, one of your algorithms, capital A, one of your algorithms from your class has the best average performance. You're going to declare victory if our average performance over time is the same as that of the best fixed algorithm in hindsight up to an error term that's going to 0 with capital T. That's what we mean by achieving vanishing regret, and that's what we'd like our online learning algorithm to accomplish. This probably should seem like a familiar problem, like maybe this is well solved by off-the-shelf algorithms like weighted majority or multiplicative weights. That would be true if you were just thinking about 7 SAT solvers or a finite set of algorithms. But if you have an infinite or uncountable number of algorithms corresponding to an infinite number of actions, it's not even immediately obvious how these algorithms would be defined. Your response might be, yeah, but I kind of feel like I've seen, people get nice regret minimization results when you had an infinite set of actions. And yes, you did, but there was always a Lipschitz condition in the background playing a role. And as I discussed a couple slides ago, we fundamentally do not have any nice Lipschitz properties for these algorithm learning questions that we're looking at. So that's why the off-the-shelf techniques don't work. And it's not just that the standard techniques don't work, it's that we actually have an impossibility results. We can actually show that you can't get what you want in the normal sense of the word. So no online learning algorithm, it's information theoretic lower bound. No matter how smart you are, no online learning algorithm can get any non-trivial approximation guarantee with respect to that benchmark. And as you'd expect, this example crucially exploits the non-Lipschitzness of the function class that we're dealing with. The good news is that actually we were able to draw on a different tool from the Beyond Worst Case toolbox and recover a positive result. So we did a smooth analysis, smooth in the sense of Spielman and Tang. So here the adversary can again pick whatever graph it wants. It can pick whatever vertex weights it wants. But those vertex weights get slightly perturbed by nature before that instance is passed to the learning algorithm. And what we can show is that, that sort of little bit of randomness in the input actually, on a technical level, has the role of compensating for the lack of Lipschitzness. It's sort of like we get it back in a smooth sense. And for that reason, we can, in fact, get vanishing regret as the time horizon goes to infinity. So again, this work's now a few years old. There's been really nice work that's followed ours. I don't really have time to survey it in detail. Again, I think Nina Balkin's chapter in the Beyond Worst Case book is probably the best entry point for that. Wrap up with a couple open questions. Last slide. So my emphasis here has not really been on computational efficiency. I meant to say earlier that whenever you do get a running time of your learning algorithm, which is only exponential in the pseudodimension. So when you have a class where your pseudodimension is logarithmic, like it was for our greedy algorithms, you actually get a polynomial time learning algorithm. It's sort of a brute force algorithm, but it does run in polynomial time. So it would be interesting to know whether there are non-trivial learning algorithms. Can you beat brute force search with a learning algorithm? Or I think probably more plausibly, under suitable complexity assumptions, can you rule out beating brute force learning? That I think would be super interesting. Something in the paper I didn't have time to tell you about is we do actually do a sample complexity analysis of gradient descent with respect to learning the best step size to minimize the number of iterations until convergence. We view that as really just sort of a baby result toward what's hopefully a much more general theory to really give guidance to hyperparameter optimization. So that's another direction where I think there's tons one could do, and I think it's potentially a very high impact outcome of this line of work. And finally, obviously, as sort of algorithms and complexity people, we have many notions of what it means for an algorithm to be simple or complex. Here we have a statistical one, not really of a single algorithm, but of a family of algorithms being simple or complex. It'd be very cool if there were any non-trivial connections between these statistical notions of complexity and the more traditional algorithmic ones that we're used to. So I'm out of time. Let me stop there. Very happy to take questions. Thanks.
Thanks, Tim.
Thanks, Tim. So let's see. So we have a few minutes to handle questions. I mean, there's a bunch of questions in the Q&A panel. Like I don't know, Sergey, do you want to?
Maybe I'll read it and cherry pick.
Okay, perfect.
Does that sound good? Or?
Yeah, just keep in mind that I answered some of them by punting them to the end, right? So there are both in the open section and in the answered.
Yeah. I do see the peanut butter and chocolate might have been a reference appropriate for people of a certain age growing up in a particular part of the world. But, let's see. So as far as the impossibility result, we only prove, so this is the question by Vasilis Livanos. So we only prove it in the paper, the impossibility result for the max weight independent set problem. But if you read it, you figure you could surely do it for lots of other combinatorial optimization problems as well. I mean, the construction is kind of annoyingly problem specific. There's like a clever combinatorial construction, but you would expect that other NP-hard problems you could do something similar as well. So thanks for that question. Right, so to Demaya's point, answer the first question, can the proof be interpreted as showing that the Lipschitz property you were looking for is indeed true, except that poly n values of P, which represent transition points for the comparisons? That's exactly right. In fact, the theory developed by Balkin, Dick, and Vittersik and others, they make that really precise. So they really tease out exactly what it is we were using to get our results. And it really is about basically having piecewise Lipschitz functions with not too many pieces. So that's an excellent comment. So again, I would check out Balkin's chapter in the book for details on that. It's a really nice theory, in my opinion. I really like what they did. So Anna Thomas asks about the empirical performance models for algorithm selection. Is there any theory regarding what types of problems admit a compact set of features that are sufficient to solve the problem efficiently? That's a great question. So really, it's kind of like it's almost like a feature selection problem, but even more fundamentally about possibility versus impossibility. So when can you actually have kind of a succinct summary that actually would? So the one thing to remember, I guess, is you have to, do you phrase the question with respect to a fixed algorithm, or are you trying to actually phrase the question with respect to the stat problem itself? The second one, seems more challenging to me. I suspect complexity theorists might have some lower bounds there on what could be done. I think what's more interesting is if you, from the algorithmic side, is what if you actually had a fixed algorithm you really cared about, and you just wanted features sufficient to explain what that algorithm is going to do. That I've actually never really seen work on, and I think that's a fantastic question. I really like that question. Yossi Azar writes, was the degree the original degree or the current degree? Good question. The way I explained it in the talk, it was the original degree, but you can carry out the analysis also with the current degree if you want to use an adaptive independent set heuristic. All that changes is that the hidden constant in the big O of log n gets a little bit bigger. Right, so Chandra points out that there seems to be sort of a difference between example 2 and examples 1 and 3. So example 2, which was SATzilla, you weren't pre-committing to an algorithm, you were pre-committing, sorry, you weren't pre-committing to an algorithm, you were picking an algorithm on a per instance basis. The formalism in the paper actually kind of handles both in the same way. So the SATzilla example would just correspond to pre-committing to a mapping from SAT instances to algorithms. So again, so in other words, sort of once you've sort of fixed the 7 SAT solvers and you've fixed your 7 statistical models, you know, at that point you can think that you have committed to an algorithm, even though the algorithm you've committed to will itself be using 7 different subroutines. So as you'd expect, you know, the sample complexity does blow up some if you're doing this sort of, you know, feature-based learning on an per input basis, but the theory we developed still gives you sort of the right kind of sample complexity balance. All right, so I think I should probably stop there, or I don't want to take too much of Edith's time. So.
All right, Cooper, super. Thanks a lot, Tim. And that's
maybe can I just say quickly that if I'm happy to I'll be here the whole workshop. So if you want to communicate over chat, you know, or feel free to ask me afterwards as well. Very happy to talk more about the work.
Cool. Thanks again. So I forgot who's chairing the session now.
I think I'm chairing, but Piotr, I think you're doing a fantastic job. So you should go ahead and do it.
No, you go ahead. You go ahead.
All right. Well, you know, so I guess we have to make an executive decision here. So what are we doing? So I think that the next talk is scheduled to start, I think, at 11. So what do we want to do? Do you want to do you want to start now, or do you want to wait a few minutes and start at 11?
No, so actually, the next talk is supposed to start 3 minutes ago, I think.
Oh, 3 minutes ago. Okay, perfect. Okay, sorry. Okay, good. So we're good. So we're late, so that means that we're in time. All right. So yeah. So for the next talk, we have Edith Cohen, who's done phenomenal work kind of for quite a while in machine learning and of course in algorithms. So it's a delight to have her here in the workshop. So yeah, super excited to hear Edith's talk. Edith, I think you're on mute.
Okay, can you hear me now?
Yeah, perfect.
Okay, thank you, Yaron, for the generous introduction, and thank you, the organizers, for inviting me. This is very exciting. So I will talk today about recent joint work that will appear at ICML. And this is with a student at Stanford, Ophir Gary, who will be graduating in a year, and with Rasmus Pei, that you probably all know. Okay. So I will not talk much about Beyond Worst Case because there was a lot of introduction already. I'm a big believer in this type of approach because over the years I've seen it very useful many times. In this work, I will talk about one problem, the problem of weighted sampling of streamed and distributed data according to function of frequency. And beyond worst case aspect is that some really useful functions require large sketches in the worst case, polynomial size sketches. And we will see approaches to get around that. Okay. So, okay, so I will start with some review of weighted random sampling, and then we'll talk on the specific streaming type model. Okay, so for random weighted sampling, we think of a data set of key value pairs. And we will, for the purposes of this talk, we will think of random sample as some subset of the keys. And for the keys in the sample, we have the weight. And we also can compute in some way the probability that they are included in the sample. So there are many sample schemes that can be thought of as being in this form. So, and then if we have the sample in this form, we can get unbiased estimation. For example, if we look at each key X and we want an unbiased estimate of a function of its weight, so we can just use the inverse probability estimator. So we apply the functions to the weight and then we divide it by the probability that the key is included in the sample. And so if the key is in the sample, we get an estimate that is larger than the weight, but if the key is not in the sample, the estimate is 0. And that way the estimate come out to be unbiased. So what are the uses? So like data, big data, machine learning type of uses for this type of, for samples. So for once, the sample can be used as the sparse representation of the data of keys and associated with the functions of the frequencies. It's a sparse representation of this vector where the number of non-zero entries is just the number of the size of your sample. And unbiasedness is important for many reasons. For example, stochastic gradients are unbiased. And also the sample can be used to generally to get an unbiased estimate of statistics, any statistics of this type of form that is a sum statistics, sum over the keys of some function that depends only of what the key is, something that we have multiplied by the function of the weight of the key. So these estimates can just be obtained by summing the per key estimates over the keys that are in the sample, and then they are unbiased. So this is a really incredibly powerful, although simple, general tool. So, okay, so what can we say about the estimation quality? So this is the inverse probability estimate. So we can compute the variance of each key. It's a straightforward calculation. And as an overall quality measure of the sampling scheme, we can look at the sum of the variance of our all keys in the data set. So if we want to minimize that for a particular function of frequency, particular function of the weight, F, then there is a standard way to do that, decades old, mid last century, which is a probability proportional to size sampling. So basically we want the inclusion probabilities in the sample to be proportional to the function of the weight that we want to use. And if we do that, we minimize the sum of the variance for each key. And we can say things like the variance of each key is always at most 1 over the sample size times the function of the weight times the norm, the F norm, kind of the sum of the F values of all the keys. And if we want to, and the sum is at most 1 over k times the norm. So we get this property. So again, what does it mean? So many of these sample schemes would give you a 0 negative covariances between the estimates for different keys. So it means that if we want to estimate the sum of the F of the weights over some subpopulation of the keys, then we get this bound on the variance. Okay, and it means that if we want to use this sampling scheme, for example, to estimate the full sum, the F statistics, then we get, with the sample size, the 1 over epsilon square, we get basically relative error of epsilon. So, okay, so this is a very simple standard tool. So a really nice property of this tool is that if we don't use the exact PPS probabilities, we can still get good results. So, okay, so if we want to sample proportionally to size to minimize the sum of variances, then basically the base sampling probabilities are the function of the weight applied of the key divided by the sum of overall. And then we get the guarantees we talked about. But what happens if we use different sampling probabilities, not exactly the PPS probabilities? Then we pay some cost on the variance. So for each key, the cost is exactly proportional to how much we undersample. And then for the sum, we call it the overhead, and the overhead is basically the maximum over keys of that ratio, of how much of the maximum amount we undersample kind of a key with respect to the PPS probabilities. And what does it basically means? It means that anything we could do with, anything we could estimate with a perfect PPS sample for F that is according to P, we can still obtain the same quality of estimates if we use Q, but only we need to increase the size of the sample by this overhead, HPQ. So this is very nice because we do not compromise the quality of the estimates that we get. We only need to increase the sample by some amount. So this is very nice, and and in general, it's kind of like magic in a sense. So basically, to know how far we are off, and it doesn't matter what we're doing with the sample, we just need to kind of look at this overhead factor. Okay, so the model we're talking about here is the standard classic model of streamed and distributed data. So here we have, we think of it as data elements, which are key and value pairs. But here, multiple elements can have the same key. And the frequency of a key is defined as the sum over all elements with that key of the value of that element. So, for example, on the small data set here on the top right, the weight of the key X is 3 plus 2 plus 1, which is 6, and the weight of key Y is -1 plus 4, which is 3. So generally, we look at the data as the key frequency pairs. For each key, there is its frequency. And the only difference is that this table is not like explicit to us. So many data sets in practice have this type of form, search queries, gradient updates, training examples, views, and we want to be able to summarize this data or compute all sorts of statistics over this data from samples. So, okay, so what we're looking at is not at specific functions of the frequency. For example, for function of frequency, which is a third power, we look at this table. And for a function of frequency, another function of frequency is log. So we consider, and we will basically consider computing weighted samples according to these functions of frequency. Okay. So, we can't efficiently compute these tables. So usually what people use for this is the composable sketches, which are data structures that kind of facilitate efficient aggregation over this type of Sternberg distributed data. So, so just in short, so we want to be able to compute the sketch over some part of the data and compute another sketch over some other part of the data, and then merge the two sketches to compute a sketch of the union of the data set. Or we want to be able to see a new data element, that's for streaming, and have a sketch of the data sets and kind of obtain a sketch of the data sets plus the element from the sketch of the data and the elements. And the size of the sketch determines the communication, if it's a distributed computation, or it determines the storage, if it's streaming, and we want it to be very small. So we cannot compute this table of key frequency pairs and work with that. Ideally, for the task of sampling, we want the sketch size to be about the same as the sample size. Okay, and the question that I've been asked over many decades is which functions of frequency we can support. And this is some representative sample of prior results. So prior results, kind of think of it as easy functions, and where you can do it. And I'm talking now about the task of weighted sampling and the task of estimating frequency statistics, which is a special case, but they are kind of about the same complexity. Easy functions are such that you can do with approximately sketch size that is about the sample size. And some examples are distinct sampling, or a sampling proportional to the frequency, L1 sampling, or LP sampling, when P is between 0 and 2, and some other functions, capping functions, concave sublinear functions. So all these functions we can do with a sketch size that is about the sample size. And then there are functions that are considered hard. What is hard is that the sketch size is a kind of a polynomial in the number of distinct keys in the data set. And that's in the worst case. And some examples of pretty useful functions that unfortunately are hard are the high moments, W to the P when the P is larger than 2, and the threshold functions, the number of keys that have frequency above some threshold. So this is very useful to understand the size distribution in the data set. People interested in flow size distribution, for example, for network data, or number of request distribution for resources and so on. Or a version of this function multiplied by the wide frequency, which is the total load of frequent keys. Okay, so these functions are very useful, but they are hard. They require, in the worst case, polynomial size sketches. And in this work, we try to understand if it's real, when we can do something about it. So these hardness results, the lower bound, are derived, of course, for worst case instances, and the practical instances are often different. And the question is, in which practical instances we can, cases we can do better. We can design sketches for these hard functions. And there were two approaches that are kind of explored. The first approach is here in a paper by Ali and Piotr and others. And there was some follow-up work, which is where you have a machine learned advice. So you have some predictions on the frequencies of items, and you can use it. And then a second approach is to assume a realistic input distribution, not assume the worst case distributions. And the first time I've seen this approach taken is in the count sketch paper of Moses and others, and Chen and Farah Colton. And there they actually also looked at what happens with Zipf's distribution. So in Zipf's distribution, they observed that the heaviest keys are actually heavy hitters. So so actually count sketch kind of works for them. And usually heaviest keys are a hard problem. It's a threshold problem. So, so our particular approach here is, instead of looking at a specific function of frequency f and the worst case frequencies for that f, we look at the combinations that work of a function of frequency and the family of frequency distributions for which small sketches can work. Okay, so let's see what we can do with machine learned advice. So the model, it's very similar to the model of Piotr and Ali, and is that when we see a key X, we can immediately ask the model and we can get a prediction AX of its frequency. And this prediction would normally be based on past data and for which machine learning model was applied to. So the algorithm we propose is basically to do a weighted sampling according to the function applied to the predicted frequency. And this is a much easier problem because you don't need to, because whenever you see even one instance of the key, you have that prediction of the frequency and you can apply F. And and basically you can apply any simple sampling scheme and sample according to this function of the predictions for even hard functions. For the keys that we sample, it's easy to keep track of their actual frequencies in the data set, which we do that. And we combine it with a uniform sample. basically for unbiasedness, so that each key has some positive probability to be sampled, and it also gives us some robustness. And the guarantees that we can get depend on the accuracy of the advice, like we like it to be. So basically, if our estimates of the advice are within a factor C of the actual value, we can emulate a sample, the actual sample according to f of the frequencies with overhead C. So if we sample according to the advice, that emulates, it's as good, a sample of a certain size is as good as a sample, as a perfect sample that is a fraction C of the size. So, and then the combination with uniform allows us to relax this a little bit and say that we only need this relative guarantee when the function f of the frequency is high enough, is more than average. For the very infrequent keys, we don't care because uniform covers them, and we will not undersample them in some settings. So these are the guarantees we get for the advice. And then we try to run it, and on the advice model we got from Su et al. That's the work with Ali and Piotr. So we also tried two standard sampling schemes, L1 and L2 with and without replacement sampling as a reference. And the green line here is kind of the error bounds, the guarantees error bounds that we would get if we sampled perfectly, but use the bound that holds for any distribution. So we can see that the advice does pretty well. That's the purple line. It does better than L1 sampling, initially at least, for a pretty reasonable, until the sample size gets larger. But L2 sampling kind of beats it. Even L2 sampling without replacement seems to beat it on this data set. And this is another data set where it seems that also for the advice performs worse than just simple simple L1, sorry, and the L2 sampling. So I must say that here we kind of insist on unbiased estimation. If instead we decided to throw away keys that the advice doesn't capture well, we would, we would get biased low estimates, but maybe they would be closer to the actual value. We didn't try that, but this is what we had seen. And here the advice is taken from past data of the same data set. This is a stack overflow data set. Okay, so okay, so the question is why is that? And that kind of brings us to the second part. The second approach is to look at the frequency function combinations. So the classic approach is to consider a sketch, a sampling sketch for a specific function that should work. Its size should be such that it should work for any possible set of input frequencies. And here we kind of try to restrict the set of input frequencies and broaden the family of functions that we can handle. And what we did is just use some off-the-shelf sampling sketches, those that sometimes are already implemented in many places or are known to work well, like L1 and L2 sampling. And what we are asking is this type of questions. How well does our sampling scheme, L2 or L1 sampling, emulate F sampling for the particular families of input frequencies. So in general, the overheads would be very large if we don't restrict the input frequencies. We know that because of the lower bounds, but maybe we can do better. So this is some flavor of the type of results we can get. So here we look at how good are L1 or L2 samples in estimating high moments or sampling according to high moments. So here we have the following kind of result. If our input frequency distribution has an LQ epsilon heavy hitter, and what this means is that the maximum frequency to the power of Q is at least epsilon of the total Q norm to the Q of the data set. Then for any, so think of Q as a 1 or 2. Then for or it should be, then an LP sample for any P that is larger than Q, 3, 4, 7, all the hard stuff is emulated by an LQ sample with overhead that is at most 1 over epsilon. So for example, if our input frequencies are L1 epsilon heavy hitter, then an L1 sample works great for all the high moments, all the hard high moments, with overhead that is just 1 over epsilon. So this is actually pretty strong because the high moments are very hard, and requiring a distribution to have an epsilon heavy hitter is not a huge requirement. Like almost all practical data sets, the heaviest elements is some fraction of the total weight yeah. So for example, if the input frequencies are zipped with parameter alpha for alpha larger than 1, and we use L2 sampling, the overhead is only 1.65. At most, it's smaller for larger alpha, actually. And then if alpha is larger than 2, L1 sampling suffices. So the proof here is very simple. It's basically just putting everything together. So basically, the ratio in the overhead computation is maximized on the most frequent elements. And we kind of just look at that. And this is, for example, what we get on some real data sets if we try to estimate third moment, and normally hard function with L1 and L2 schemes. So without replacement schemes always do better than with replacement schemes. And L2 is better than getting the heavy keys, but L1 kind of is more representative. But and also the L1 here is without replacement. So normally you would expect L2 to do better for third moments than L1, but here the L1 is without replacement. So we get a pretty good results. The green line again is the upper bound of what we want to see with a good sample. And we are much better than it. So here is another kind of results that we get. So this is even much stronger, but it's for a more restricted family of distributions. So here we look at the universal emulation. So we want a sample that basically would emulate well sampling with respect to any monotone and decreasing function of the frequency. So that's a huge family of functions. It includes all thresholds. So if we don't worry, if we're not like in this streaming distributed kind of model, there is a simple way to do it, a simple sampling probabilities that do it. Basically, what we want to do is sample the ith most frequent key with kind of probability proportional to 1 over I. So the HI here is basically the harmonic number, it's just to normalize it. So the probabilities add to 1. And then we get, basically this allows us to emulate kind of all threshold functions, and then that would cover all monotone functions if we can do all that. Basically, that's kind of the argument. And the overhead is only log n. It comes from that harmonic term. So, but the problem is this we cannot do with in the streaming kind of setting, because otherwise we would be able to get everything, high moments, thresholds, everything always. So what we can show is that if the distribution behaves like this, with alpha bigger than half, then LQ sampling with a Q which is 1 over alpha, which would be larger than 2, which we can do, is gives you actually a universal sample for that frequency distribution. And if we can do a sample that kind of covers all LP samples between 0 and 2, which we can do with logarithmic overhead, that would cover all ZIPS distributions that are larger than half. That means we can estimate any monotone function of frequency well for them. Okay, so this is so to get this result, we needed to restrict more the family of functions. Before we just needed a heavy hitter. Here we kind of to have this, we need the tail not to drop too fast. So, but this is the type of level of result that we get. And here are some experiments. So this is basically using a simple sample, L1 or L2 samples with without replacement. This is just estimates from one sample. And to estimate the rank versus frequency distribution. So the x-axis are kind of the keys. And for every number, like say 5, it shows you the number, I think it's the number of keys that for every weight on the left, for every frequency on the y-axis, it shows you the number of keys. The corresponding point is the number of keys, estimate of the number of keys that are at least that frequency. So, so the blue line is the actual distribution. And then the other lines are the estimates, and we can see that without replacement samples kind of get you deeper, but we can see that, and we can see that L2 kind of is better estimates on the head, on the heavy rate items as we expect than the L1 sampling, but basically we get pretty good results here. And this is a hard problem. These are kind of samples of the types of overheads that we get. So we actually here computed the overhead for particular data sets with L1 and L2 samplings. So to emulate L3 sample by L2 samples on these data sets, we get really small numbers between 1 and 4. To emulate an L10 sample by L2 sample is also pretty small, and universal emulation is also not as bad as one would think. You need a sample size larger than a few hundreds, but it's tolerable for what it gives you. Okay, so conclusion, just a summary of what we said. So normally this type of composable sampling sketches are limited by hardness results, and we consider the 2 beyond case scenarios that the advice and the frequency functions combinations that seem to give promising results. So I think I'm a bit over time, so thank you. Yeah.
Perfect, thanks.
Yeah, it's always hard to go after a team, but yeah.
Great. No, thanks. Thanks for the fantastic talk. This is super fascinating. Yeah, like you said, we're pretty much almost pretty much on time. So, does anybody have any questions that they want to ask? I have a couple. Okay, good. So I'll just be selfish and go ahead. So Edith, I'm wondering whether, and maybe this is also kind of like a broader question, but so from, if you sort of, I think that this work largely focuses on the algorithm design aspect of it, but if you kind of think about the machine learning aspect of it and trying to think about, basically better prediction algorithms kind of to construct this oracle, like, are there any kind of, are there any thoughts there? Or are there any thoughts on like how we should be designing these, because these are kind of would be kind of these would be algorithms I'm assuming that people haven't worked, like kind of prediction algorithms people haven't thought about a lot. So any thoughts on like what we could do there, given that we know what algorithms we're using?
Well, usually, okay, I mean, I don't know about the machine learning aspects, but what I observed is that usually these types of data comes from some sources, and repeatedly we do the same thing for similar data. So we can just kind of understand properties, model it. I mean, so what works well yesterday, the kind of settings, based predictions of past data can help now. I can't say anything more intelligent. There are so many machine learning models, sometimes just simple statistical models do a lot of the work well. Yeah, I don't know.
So maybe not doesn't sound like it's a fruitful avenue. That's interesting. Okay. Cool. Okay. Okay, great. So I think that we're running out of time. So thanks again for Edith. And again, we can take more questions like offline in the chats and the Q&A.
Okay. Thank you.
I guess we. Great. So according to the schedule, now we have a. Sorry,
we are in break, so we have 8 minutes.
Yes.
We start at 2:40. I mean Eastern time.
Okay, sounds good. So everybody has time to go to the restroom or do kind of all the things that they need to do. They need to, we can get coffee and chat offline. Okay, so we'll resume in 8 minutes. See everyone.
Okay, so people are joining, so maybe we can start.
Should I start?
Let me maybe just wait. I'm kind of start. Yeah. So our next speaker is Ravi Kumar. He has done several great work in this area, and today he's going to talk about online learning. His work on online learning. Okay, go ahead.
Thank you. I'm just trying to find out how to remove the side panel. Okay, good. Good. Hi. Thanks to the organizers for inviting me. It's a great workshop, and it's very timely, and I'm really excited to be working in this area. So the work I'm going to present today is on online learning, and it fits with the theme of the workshop, which is I'm going to discuss about how to involve machine learning oracles inside online learning. So this is joint work with Aditya, who's at University of Utah, Ashok, who's at Google and is going to join BU very soon, and Manish, who's at Google. Okay. So I noticed that from the workshop, other talks, none of the talks actually talked about online algorithms. I could be wrong. Maybe Michael is going to bring about that. But what I wanted to briefly discuss is like how online algorithms fit with the whole theme of machine learned oracles. So online algorithms are a great way to abstract decision making under uncertainty. So in this model, you have inputs coming one by one, and an algorithm has to take a look at the input and make an irrevocable decision. For example, a classic example is caching, where pages arrive one by one, and an algorithm is supposed to decide whether a page resides in a cache or not. And there are several ways to measure the performance of the algorithm. There are two very popular and extremely robust ways of measuring. The first is comparative ratio. I'm sure all of you are familiar with that. the notion is to measure the performance of an online algorithm against the best offline algorithm. So the offline algorithm knows all the future inputs that are going to arrive, and we measure the worst case performance of an online against the best offline. There is a different notion that's been used, especially in the online prediction setting. It's the regret. In fact, Tim touched upon that earlier in his talk. There, the goal is to measure the performance of the online algorithm against a class of benchmarks. You can think of the benchmarks as defining a restricted amount of restricted notion of algorithmic class, and I want to compare the performance of my online algorithm against the best one from this class. And as I mentioned earlier, online algorithms are a great way to model unknown future, and they are another classic example of trying to mitigate uncertainty and going beyond worst case analysis. Okay, so how does learning fit into this framework? The question of interest here is, can one improve the performance of online algorithms when there is some information about the future? The key thing to notice here is that the information that's available about the future could be possibly wrong. So think of there is a prediction or advice or a hint, whatever term you want to use, available, and the algorithm, before it makes a decision, gets to use this prediction or the hint, and hopefully the hint can serve to improve the performance of the algorithm. That's the whole theme in this area. And there are various ways to model the future, and in fact, most of them are actually problem specific. One way to model is bounded look ahead. So in caching for the last many years, people have looked at what if instead of assuming pages arrive one by one, I get to see the next 3 pages available in the future. Can I improve the performance of caching if I have this bounded look ahead? That's one specific model. And more recently, people have built machine learned models that can give an idea of the future. Like, so this has been used in a bunch of work recently, including scheduling, caching, and ski rental. There, the idea is use a machine learned model to indicate some things about the future, maybe which page is going to arrive next, or whether I'm going to ski for how many days, or what is the expected size of the job that's going to arrive next. That's another paradigm that's been used recently. And the third kind of modeling, a way to model the future is what we call actually semi-online, where the future consists of a known part, a part that's available to the algorithm, and there is a part that's not known to the algorithm. Think of it as being adversarial or stochastic. And a bunch of problems have been studied in this model, including bipartite matching, some allocation problems, some caching, and some interesting results are known in this setting. And the fourth kind of way to model the future is having some kind of extra auxiliary information. The information may not be directly relevant to directly obvious to the problem we are solving, but it could be helpful to solve the problem in an efficient way. For example, there was some nice work by Sergey and his co-authors this year actually on scheduling, which kind of fits into this framework. And there is a fifth bullet for somehow the slides are missing, is there is a small area in complexity called advice complexity, where the goal is to quantify the amount of information that one needs to know about in the future in order to be able to solve a problem. And people have studied a variety of problems, including online shortest path and independent set, and of course caching and so on in this setting. And the goal there is to say, okay, if there's an algorithm, a deterministic algorithm, if I know 3 bits about the future, then it's enough to beat the K bound and so on. But we won't go into that. We'll try to focus mostly on the ML version of this model, but the reason why I put up this slide is to say that there is some leeway into how the future can be modeled. Okay. So given that we are dealing with ML models, since ML models by definition come with some notion of error and the algorithms have to be robust in some way, there are 2 important points to keep in mind to make our algorithms actually meaningful. The first notion of consistency. There the question is, how well does the online algorithm perform when the hint is good? In an ideal setting, we want since we're talking about online algorithms, we want a near offline performance when the hints are really good. That's to be expected, right? I mean, we want the hints to be helpful, and we want the algorithm to fully take advantage of the hints and improve its performance. And there's also this complementary notion called robustness. There, the requirement is somewhat asymmetric. Here we want the algorithm to perform. We want to understand how the algorithm performs even when the hint is bad. And in an ideal setting, what we want is actually a near online performance, even if every hint is bad. Suppose the hints can be adversarial or really bad or could be misleading. Even then, we want the algorithm to gracefully degrade in terms of performance. And that's something that's this required of an ML augmented algorithm. So in this setting of consistency and robustness, many combinatorial optimization problems have been studied in the last especially like 3-4 years, and excellent algorithms are known, and many of them are studied with a competitive ratio as a metric in mind. And these algorithms are consistent and robust, and even very tight bounds are known in terms of the consistency and robustness, the trade-offs between them, and what can be done in this setting. So I won't go into the details. I'll refer to the survey by Michael and Sergey. They should have enough context. The question that we address in this talk is, what about regret? That's another natural online performance metric. And what about problems like online prediction, where regret makes sense, and how would ML augmented algorithms actually look in this context? So to be able to study this, we take this classic online optimization game. This was actually formalized not so long ago, if you think about it, by Marty Zinkovich in 2003. And once again, many of you may be very familiar with this setup. Pardon me if I'm overdoing it, but here is how it looks. So the algorithm takes place as usual in an online setting, so it goes in rounds. And in the Tth round, the algorithm chooses a vector, say WT, belonging to some space, say W. And the system returns a loss function, which takes a look at this W, and then returns like a real number. And the loss at this step is exactly applying this loss function on the algorithm on the vector I chose. And then you sum this loss over all the time steps, and that's the loss of my algorithm. That's hopefully that's clear. And this picture is supposed to reveal that. So we have weights or vectors predicted at every step, and the loss function is revealed after I make the prediction and I accumulate this loss step by step. And the objective here is minimizing regret. And what do we mean by regret is, I want to compare against the best fixed W star in hindsight. I mean, that's a benchmark we are comparing against, right? So you want to take the difference of the loss of the algorithm, sum over all T of loss of the loss at every step, minus the sum of the loss if the fixed vector W star were used by the perfect algorithm. And that's the quantity that we would like to minimize. That's called the regret. Okay. And why is this setup even interesting? It looks like very simple and very natural. Actually, it can model a lot of very important, interesting problems. And I'm not going to be able to do justice to this, but please take a look at the book by Elad, and it has a nice compilation of all the applications. So for example, this framework can model online shortest paths, matrix completion and recommendations, portfolio selection, and expert advice, and so on. And of course, the key thing to keep is that the loss functions should have some structure. And if the loss functions are chosen adversarially, then basically you can't do anything. So they need to come from a class or have some structure, some special things about it. And a typical structure that's being imposed on the loss function is that they can be convex, or they can be strongly convex. And imagine strongly convex as something growing faster than a quadratic, or it can be linear, and so on. So that's a restriction of the class that people mostly apply to study this setting. So in this work, we'll even restrict this class. We'll look at only the linear optimization setting, and we'll see why it's actually interesting. And in fact, for the first part, we'll only look at the constrained version of the problem. And here is the formal definition. So imagine the unit ball in D dimensions, all the vectors that have norm at most 1. And the framework is as before. At every step, the algorithm has to choose a vector WT, but the WT is supposed to be inside this ball. And the system reveals a cost vector CT, and the loss function is linear. It's just the inner product of the weight vector and the reveal cost vector. Okay? So it's just inner product of WT comma CT. And the constraint online linear optimization objective is to minimize regret, and the regret definition is the same as before, except that since we know the loss function, we can actually plug in the definition. So it's maximum over all like hidden or magic vectors W star of the regret of the algorithm minus the regret if you were to use W star. It's the best possible W star. Okay, and in particular, this framework, you might think, okay, it's very special, the linear function, but it can capture a lot of very interesting problems. For example, it captures stochastic optimization, because imagine an algorithm that's trying to minimize a function. It progresses through the space by choosing a vector WT at every point, hoping to get to the minimum, and the system reveals a cost which is like the gradient taken at this current choice of the, and the loss function is like the gradient taken at the current choice of the algorithm. And when we try to minimize regret, we are implicitly trying to approach the optimum of the function. And that's where the notion of sublinear regret bounds makes sense. So sublinear regret bounds means that the average performance approaches a fixed benchmark. So any regret bound that's little o of t is a sublinear regret bound. And in stochastic optimization setting, it makes sense because what it means is the algorithm actually converges to the optimum as you let it run. Okay? And the classic regret bounds, if you look into the original work of Marty, and also the tight bounds were known by Cesar Bianchi and Lugosi, argue that the regret is actually square root t. And that's a classic result. And in fact, the gradient descent step gets you the upper bound of square root t. And it turns out that if the loss function is linear, this bounds are tight. And in fact, they are the hardest for this class actually. Linear loss functions are the hardest. We'll come back to this a little bit later. Okay. This is the story behind sublinear regret bounds. Okay. And the question that we ask is, okay, we got sublinear square root t regret. Of course, we get even smaller quantities, the better it's for our algorithm. The question is, how much can we improve this regret? Can we go beyond sublinear? Okay. So what has been done here? So it turns out if the loss function has additional properties, stronger properties, like for example, it's strongly convex, there is a very beautiful result of Elad and his co-authors that argue that you can get logarithmic regret. Okay. So remember, strongly convex means basically it's growing faster than a quadratic. Okay. And this plus the fact that the linear case is like omega square root t says that the linear case is the hardest. Therefore, we are kind of justified looking at the linear case because we want to solve the hardest problem in this class. Okay. So that's one case where a sublinear regret is known. There's another interesting case which the authors called it adaptive regret bounds, where, like as Tim was pointing out earlier, the regret bound is expressed in terms of the underlying data, if you can think about it, right? So the regret bound is basically the L2 norm of the cost vectors. Therefore, I can hope to get a substantially smaller regret if the cost vectors are small in magnitude. That's another case where you can get small, less than like square root t regret. Of course, these are very special cases, and we would like to go even better. Like, the question is, can we do even better? Can we go beyond these cases? Okay. And that's a question we study in this work. And in line with the theme of the workshop, we ask the question, what if every step has access to a hint? So think of this hint as being supplied by like a machine learning oracle, or maybe some other mechanism gives the hint to the algorithm. But in any case, the framework looks in the following way. And this is how constrained linear optimization looks with hints. So same framework remains, except that before choosing a vector to respond or to play, the algorithm has access to a hint, ht. And since it's a constrained case, we assume that the hint also lies in this unit ball. Okay. So the picture shows you an idea. So you have, before the algorithm responds to the vector, so it has hints available. And we can assume that the hints also appear online. It doesn't really matter. We don't really use the future hints, but you can assume that the hints actually arrive one by one just before the algorithm gets to respond. Okay. Of course, the rest of the steps remain the same. The cost vector arrives as before after I respond, and the loss is the same as before. It's still the linear loss, and the regret definitions remain, except that the algorithm has access to some idea of a hint. And the question is what to do with the hints. Okay. And again, what do we seek of such a framework? So we want two properties as before. So we want the regret to be low if the hints are useful. And we want the algorithm to degrade gracefully if the hints are bad. The hints, remember, can be really bad or adversarial. So formalizing a little bit more, by consistency, we mean that the algorithm should get something like little o of t regret if the hints are reasonably good. The hints are like, guaranteed to be good, then we want reasonably substantially smaller than like square root t regret. And ideally, if all the hints are good, we want something like log t regret, because that's like the holy grail for us, right? That's achieved for like strongly convex case. So we want like a logarithmic regret if all the hints are good. Conversely, even if every hint is bad and every hint is like trying to mess up the algorithm, even in that case, we never want to do worse than square root t, because we can think of an algorithm that doesn't use the hints at all, and we want to degenerate to that case if all the hints are bad. And we want to do it in a way without knowing whether the hints are good or bad to begin with. And remember, the hints can be good or bad at an individual level. It's not the case that the entire set of hints are going to be good or the entire set of hints are going to be bad. So every step, some of the hints can be good, some of the steps can have good hints, some of the steps can have like really misleading or bad hints or adversarial hints, and still we want a uniform algorithm that works in all cases. That's a setup. And the question here is, how are we going to use a hint? So this question is not new. It's been studied before, not so much couched in this language. So there is a nice work of Elad and Nimrod from way back in 2007, where the algorithm is given some partial information about the cost vector. So in particular, they show that if the first coordinate of the cost vector is available as a hint to the algorithm, and suppose it's sufficiently large, its magnitude is at least like alpha, then you can get around the square root t bound. You can actually get a logarithmic regret. The regret they show is something like d squared over alpha times log t, where alpha is the amount of information you basically give it to the algorithm, right? But as you think about it, it just gives evidence that, okay, hints are useful to help with minimizing regret, but the case is still very special. We're talking about one coordinate being available to the algorithm, and it's big. Okay. And very recently, 2017, there's another nice paper of Ofer Deckel and as co-authors that, in a way, you can think of as generalizing this setup. They look at the case where hints are correlated with the cost. So formally, we say that a hint is alpha correlated with the cost if the inner product of hint and the cost is at least alpha times the size of the cost. Okay. And what they show is that if every hint is alpha correlated, then the regret is logarithmic. It's d times log t over alpha. And alpha, of course, is the magnitude of correlation. So, of course, the more correlated their hints are with the cost, the better bound you get. And so this has a nice property that, of course, when hints are even mildly correlated, you get something non-trivial, right? You get like maybe log t regret. So it has a consistency property. Unfortunately, it doesn't have the robustness property. In particular, the method is actually somewhat brittle, in the sense that even if one hint is not alpha correlated, all guarantees are off the table. So that's exactly where we come into play. We want to understand this setup of alpha correlation, where we want some robustness as well. Okay. And there are other notions of hints being helpful to the algorithm. There is something called optimistic online learning by Sasha Racklin and Karthik, where they look at the distance version of hints instead of correlation. So they show that the regret is bounded by the distance between the cost and the hint. This is another very nice result. So it has, of course, a chance of getting square root t regret only if the hints are really close to the cost. Now imagine if every term in the summation contributes constant. At that point, I can't hope to get little of root t. So every step, or at least most steps, have to be really, really close. The hints have to be very close in distance. But on the flip side, they achieve robustness. The hints, because these are happening in a bounded ball, the hints are never worse than square root t. So they get robustness, but the consistency places too much demand on the hints. And why do I say that? Because imagine, cost is some vector in space, And the notion of closeness defines some ball around the cost vector. But correlation is much weaker notion in some sense. Now all you care about is some half space, and anything beyond half space is considered correlated, and therefore it potentially can encompass a large family of hints, which is useful in practice. Okay, and here is our main result. What we show is that if all but B hints are alpha correlated, then the regret is bounded by this quantity, which is basically root B plus root B times log T divided by alpha. Okay? And let's examine this expression, why it's both consistent and robust. Let's consider the extreme case when all the hints are good. I mean that all the hints are like alpha correlated. That's what I call it good. Which particular means the term B is 0. No, there are no bad hints. And therefore this expression reduces to log T over alpha, which is what we desired. We want a logarithmic regret. And for robustness, even if every hint is bad, B is equal to T, it turns out that the log expression actually vanishes, second expression vanishes, and we just get square root T. So we kind of fall back to the default regret bound without hints, and which is exactly what we want. That's the main result of our work. So at this point, it's good to take a step back and compare it against the previous result of Offerdekel et al. So I'm simplifying the expression. The bound that I'm putting there is like the actual bound I showed on the previous slide is slightly stronger, but for simplicity, we'll just work with this bound. So it's square root B log T over alpha, and they got like D log T over alpha. And of course, by very nature, our bound works even when there are bad hints, whereas they need every hint to be alpha correlated. So robustness is guaranteed in our case. And interestingly, our bounds are independent of the dimension actually, even if all hints are alpha correlated. Even if B is B is 0 in the previous expression, we get like log T over alpha, whereas they got like D log T over alpha. So we save a factor D in the regret. And not only we save a factor, but also our algorithm is faster by a factor T. And the proof itself is like far simpler. Okay. And in both our cases, even their case and even our case, the algorithm doesn't need to know alpha. So remember, like B is actually B sub alpha. So B is a number of places where it's not alpha correlated. So the algorithm doesn't need to know alpha. It kind of learns alpha and B sub alpha as it goes along. Okay. That's a framework. Okay. So let me quickly go over, I think I'm supposed to finish at 11, 12, 10, 12, 15 already. Yeah. So let's try to understand the expression. So we have root B log T over alpha. Let's see which of the terms are actually needed. Okay. So first of all, it's very easy to show a square root B lower bound. B is a number of bad hints. It's almost like padding argument, right? So we have a square root T a lower bound for the vanilla case. Therefore, if I pad the initial portion with all the bad hints, then algorithm will not benefit anything and put the lower bound instance there. So we get like square root B for free. But you can do something slightly more. Even if the hints are interspersed in a random way, but the hints are bad, we can come up with a simple one-dimensional example where in this case, it's like the cost vectors are numbers. So it's P minus 1 with probability P and P with probability 1 minus P. So therefore, the expected cost is 0 and the expected loss of any algorithm is 0. And the expected number of bad hints is like P times T. But in hindsight, there is a magical benchmark. In this case, just the sum of all the costs turns out to have omega square root T, does omega square root B better. So this just is a slightly different worst case. Similarly, you can also show why that 1 over alpha term is needed. So this example is slightly harder, but not too hard. So here you have to go to 2 dimensions. So imagine 2 unit vectors, E0 and E1, and the hints are always E0. The hints only talk about 1 dimension. But the costs flip between them. Now it's alpha E0 plus minus 1 minus alpha squared E1. So it's basically a combination of these 2 axes, but in a random way. The plus minus 1 is like chosen with probability half. And you can show that the expected reward of any algorithm is at most alpha t because it only sees about like one dimension. On the other hand, as in the previous case, there is like a magical benchmark that will beat this. The expected regret is alpha t minus this expression, which you can show that it's at least 1 over alpha for large enough t. So this 1 over alpha term is also needed. And if you go back, this expression looks like square root B divided by alpha times log T, and we didn't get this form. And there will be a reason for this, why we can't do this. And the only slop we have here is that we are unable to remove the log t thing in our expression, and we don't know if it's inherent. So imagine the case when all the hints are identical to the cost, in which case we should have like no regrets, but we're not able to achieve that. Okay, so let me go into the structure of our algorithm. The algorithm is very simple. So the overall framework looks like this. So we get a hint, and now that's the outer algorithm. The algorithm actually tries to play an inner algorithm that does not use a hint. This I call it script A, that's the inner algorithm. It doesn't use hint. And we use follow the regularized leader with some kind of adaptive rate as inner algorithm. So it first consults the inner algorithm and gets a vector, say W bar, from the inner algorithm. And then it combines the hint and the W bar to get the vector W, which it plays actually. So it constructs a vector W, WT, and then the cost arrives as before, and then it computes a loss, and then it sends a loss back to A. Okay, that's it kind of feeds back and forth. It gets the vector W bar from A, and it sends a loss back to A. Now, of course, I've oversimplified the presentation. We need to maintain state and so on. The rate for the algorithm A is changing and things like that. But this is the overall idea. Okay, and I'll actually give you a very quick glimpse of how the combination goes, which is the non-trivial part. For simplicity, let's assume that we know the number B. We know the bad hints. We know the number of bad hints. Okay. What we remember, like W bar is the output of the base on an algorithm that does not use hints. And the intuition is that algorithm will do really well when the hints are bad. If the hints are not very helpful, we want that algorithm to kick in. And the question now is, how do you combine this W bar and the hint? Of course, the most obvious way to combine is take W bar minus H, right? That's the easiest way. We want to minimize loss. So if somebody is giving me a hint, I just construct a new vector by just subtracting the hint. And subtracting is the right thing to do because we want the hints to be correlated with the cost vector, so it will reduce loss, right? And this step works great if the hints are well correlated. Unfortunately, that's not what we want to assume, right? We want hints, the whole thing to work even if the hints are not well correlated. Okay? So this is the first idea to reduce, the two ideas in here. Here's the first step to ensure robustness. Remember that we assume that B is known, right? So the algorithm knows B. And here is the most robust way of combining the base algorithm, the inner algorithm, and the hints. So we just construct W bar minus hints divided by square root B. So the square root B division makes sure that the algorithm is robust, because if B is really big, then I'm not going to use the hints much, right? And if B is really small, then they play a role, which is great. But remember, we simplified assuming that B is small, but I'll argue like that's not a big deal. Okay. And there's one more thing that's also violated, which is that we want the whole thing to be constrained. We want everything to happen inside a unit ball. So when I make this correction, like HT over square root B, I might end up outside the ball, and that's not desirable. So we just bring it back to the ball by just applying a careful correction. Instead of -1 HT, we just take this existing length and then use the residual as like a scale factor. Okay, and that's how we construct whatever expression I put up. WT is the one that we combine the hints. And therefore, we can compute the loss. It's a linear loss. So as you can already see, the loss consists of two parts: the loss of the base or the inner algorithm plus the loss due to the hints. Okay? That's the expression at every step. Now the question is, how do we analyze this? And that's our second ingredient actually, which is we want to somehow relate the regret of the outer algorithm that has hints with the inner algorithm that doesn't have hints. And there are several ways of doing it, but what we found is the simplest and cleanest way is to define a surrogate loss, not the real loss, but a surrogate loss that has some nice properties. Okay? And the way we're going to do it is define the surrogate loss, identify the conditions under which the surrogate loss is strongly convex, and that will automatically give us the log T bound, which is what we desire. And the definition of surrogate loss is so simple that I can actually put it up on the screen. So surrogate loss is exactly like the original loss, except that we have an absolute value on the correlation. And the key observation is that if the hints are well correlated with the cost, then you can show that the surrogate loss is strongly convex. And therefore, you get log T regret. In fact, the surrogate loss satisfies very easy, simple properties by virtue of its definition. I wouldn't go into the detail. And the first property is interesting to look at because it kind of says where the hints come into play. The cost is actually bounded, upper bounded by the surrogate loss plus some factor. Okay. And the second property says that I can relate the benchmark regret against my algorithm. So overall, the proof structure looks like this. We can relate the loss function in terms of the surrogate losses relating to the fact that they become convex when the hints are good, plus some residual terms, which is 0 if the hints are good, but it's like 1 over root b if the hints are bad. And if you sum over all the steps, you get this for free. You get like log t because of strong convexity, plus some square root b factor, divided by alpha, and plus some square root b because of the bad hints. And that's the entire proof. But here I made a crucial assumption that I assume that the b is known, but it's not a big deal. What we really do is we update our confidence in the hints as the algorithm progresses, and that is used as a scaling instead of square root b. And then we need to carefully set the adaptive rate in the inner algorithm, but it's not easy. It's not difficult. Okay. So we have a few extensions. Let me just quickly go through that. The same algorithm, in fact, actually improves the optimism bounds of Racklin and Sridharan. So by adding this extra like minus ht squared factor. And the same algorithm, actually same kind of ideas also work for the unconstrained case, where the responses and the costs are not constrained to be in like a unit ball. But of course, the regret will depend on how long you allow the benchmark vector to be, and that can be quantified. Okay, and here actually we get a stronger result. We get a result that the hints have to be well correlated only on average. Actually, you don't need for every case. And we also tried, as I said, this OLO online linear optimization is useful in stochastic optimization settings. We actually tried this algorithm in practice. This is very, very, very preliminary. It's actually only 1 week old, the whole plot is. So we tried the hints against 2 classic things like Adam and Adagrad, which are popularly used optimization heuristics and methods. And actually we are able to beat hints even for like resident 50, which is a image classification task. So we used, for hints, we used the previous gradient as a hint, but we put through our framework in order to use it. Okay. So there's some hope or some optimism in practice. Okay. So in fact, recently we obtained sharper bounds actually. So instead of the square root b log t, we actually can split this term. It's actually more like square root b plus log t over alpha. And that's the reason why our lower bounds also are of the form. We can never get like square root b times log t over alpha because you can get a sharper bound. And this sharper bound was useful to us to extend our whole result to multiple hint setting. So imagine instead of getting 1 hint, I get like k hints. And I would like to use all of them at the same time. Of course, I don't know which hint is bad at which time step. And if you use multiplicative weight updates, you get some result, which says that basically I can get the best among the k hints. But actually you can go much stronger. You can get the best linear combination of the k hints if we and express a bound in terms of the b of that linear combination. And that requires us to construct some a combiner which could be interesting. Okay. Since I'm almost out of time, I'll just summarize here. So what we did is we constructed an online linear optimization algorithm that works with hints, and it is both consistent and robust. It exploits correlation to get like sub square root t or even logarithmic regret, but in general it never does worse than an algorithm that does not actually use the hints. And in course of doing this, we also improve upon like earlier bounds on correlated hints. And I feel that this line of work opens up a lot of rich algorithmic questions. Some of it we are actually studying. We have some results, and we are also exploring the practical aspects of it. Can we actually use this to get a better, faster optimizer? And in general, I want to call this class like a P. I mean, it's not a formal definition, but I want to view this class as P to the ML. So you have this polynomial time algorithms, especially online algorithms, and we have this ML oracle, and we want to see how much this oracle can help us to improve the performance. And with that, I finish my talk. If you have any questions, please reach out to me. Thank you.
Thank you, Ravi. So if there is any questions, so actually there is one question. So there's a question that asking about the learning rate of the inner algorithm. Does it require prior knowledge of any parameters?
It's a good question. So Siddharth asked, so the inner algorithm learning rate, we actually control it. No, it's a regularized algorithm. So we supply the regularizer, and that comes from how well the hints are correlated with the previous laws and so on. So yeah. And for Devmalia's question, the hints are rich enough, could one even hope for stronger consistency properties? Bounded regrets against the best dynamic solution. So it's a good question. So it's something that we are looking at. We're looking at some dynamic regret settings to see whether whether we can actually achieve this goal. It's a good question.
So maybe the last question. So by Chandra.
It's a meta question.
Yeah. Oh, okay. Chandra is asking. Okay, so Chandra has asked a question for Edith. So Edith, if you can check the question. Okay. So is there any more question for Ravi? Okay, then, yeah, thank you, Ravi. So then I will give it to Piotr so that continue.
Cool. Yeah. So thanks, Ravi. It's my pleasure to introduce the last speaker of this session, Mike Nissenmacher. We're not really doing much of introductions in this workshops, but needless to say, Mike had lots of beautiful and cool results on the topic that we are covering in this workshop. And today he will tell us about what was the latest.
All right, thanks. Am I hearable?
Yes.
All right, let's see if we can get the slides up here. Okay. Are the slides showing up, just because? But you can see them? All right. I guess I'll go ahead and get started. So I'm going to talk about some of my past work in this area and some of the sort of updates or latest in these lines of work. So to start with, let me just say, I'm very excited about this topic or this theme. Going back through all the speakers and what Tim emphasized, traditionally algorithms have been based on worst case analysis. And of course, that's the paradigm we all know and love. And it is really let theory be what it is, that it's the right framework for a lot of theoretical results and moving forward in the way of algorithms. But for a long time, even since I was a student, I've had this nagging feeling that, it really wasn't the answer to everything, that there are always cases of people on the practical side of things coming up with things that worked, even if they couldn't prove worst case bounds on them. And so I'm a big believer in this idea of, beyond worst case analysis as described by Tim and others. And to me, it's very exciting, this idea that machine learning, offers us a new way of thinking about algorithms because of this idea that we have something that maybe we don't understand and we're allowed not to understand, but we can still use it within our algorithms in a way that's useful, but useful in the sense of theory, right? That we can actually get provable sorts of bounds. And so let me talk about first a bit about queuing theory. Queuing theory, for those who, because CS people often don't think in terms of queues, we just think in terms of scheduling. So you can think of queuing theory as, scheduling where the line goes on forever, or, people get served and new people are coming in. So it's a dynamic scheduling type problem. And also from the queuing theory side, they're a bit more welcoming or accustomed to the idea of making stochastic assumptions. And I think that's a theme that will go throughout my talk, is that maybe I'm viewing this type of analysis through a stochastic lens, and am willing to take stochastic assumptions about things like what my learning theory models will produce. All right, so just a bit of review about standard queuing models, and then I'll get to some notion of what the results are. So typically for standing queuing models, you think about Poisson arrival processes. This means that the time between arrivals is exponentially distributed, and the easiest queues also have that the service times are exponentially distributed, and the exponential distribution is memoryless, and that memoryless property ends up making certain types of analysis more natural or more simple. Particularly, like I said, when it's exponential service times, there's a lot of nice results known. In practice, of course, you don't often get nice exponential service times. You get some sort of more heavy tail distribution where a small number of jobs take up most of the service time. And in some of the simple models, or most of the simple models for queuing, it's just assumed that the service time is unknown. And this is why the idea of having things like hints for the service times are going to be useful. Some of the standard disciplines, first in, first out, which is also sometimes called first come, first serve. Just when you get in line, you wait, and then you go through. But there are others possible. We'll be looking at some that involve preemption. So maybe even though you've just come in the system, you get to hop to the front of the line if your job size is short or predicted to be short, so that you can leave the system quickly. All right, so another useful mental background note when thinking about results for what are called MM1 queues. Here the M you can think of as standing for memoryless, so MM1 queues means you have Poisson arrivals and exponentially distributed service times. And first in, first out queues, the steady state expected size in the system grows like 1 over 1 minus lambda, where lambda is the arrival rate, and we assume service times have mean 1 for convenience. Right, so the key takeaway there, or the way to think about standard queues, is that as the arrival time, as the time between arrivals and the service times, sort of match, that is, as the load gets close to 1, as the system gets as saturated as you can imagine it, you get this like very quickly steep asymptotic behavior where things slow down tremendously. So at a high level, this explains why traffic seems so bad on the freeways, and also why it's that you're always waiting in line. When you call a call center, it's because obviously from the person owning the call center's point of view, it's don't want idle resources, people not answering calls. So it's best to keep the actual service rate and the rate at which service enters as close to equal as possible. All right, so queuing theorists have obviously studied cases where you actually know the service times and looked at various sorts of scheduling. So shortest job first just means that whenever it's time to start serving a new job, you take the job with the least amount of service time and do that first. That's very natural, both in the discrete setting for scheduling, where we do the same sort of analysis, in this case here. You can have preemptive versions of this, so shortest remaining processing time says always take the job that has the smallest amount of remaining processing time left. A preemptive shortest job first says, okay, we're also going to allow preemption, but it's only going to be based on the actual job time, not on the remaining processing time. And all of these sorts of systems have known formula for Poisson arrivals and for general service time distributions. All right, so now let me finally get maybe to the subject at hand, or the subject we're here to think about, which is what can you do when you have predictions? So I want to look at the case where you have predicted service times. So we can think of it as having a machine learning algorithm that predicts the service times, and then we can consider all these policies where instead of using the actual job times, you just use the predicted job times, right? Or for shortest remaining process time, the predicted remaining service time. And hearkening back to the fact that queuing theorists are perfectly fine with stochastic assumptions, and they also tend to like results where you can get exact formula and exact answers rather than the order sort of notation results that we tend to prefer in theoretical computer science. I want to look at this through I guess, a probabilistic lens, and I will assume that there's some sort of density function that determines, the relationship between the machine learning algorithm and the true service times. So I will have a two-dimensional density function which says that, if the true service time is X, you can think of it as that gives you a distribution on the predicted service times Y. Or you can think of that density function the other way. If you're given a predicted service time Y, that determines a corresponding distribution on actual service times for the job. And that can be represented by just a two-dimensional probability density function. All right, so what is the sort of result or thing we can get? So let me first talk about, again, the case without predictions as sort of a baseline. So when we look at the shortest job first type queues, I'm not going to give a full analysis, but I'm going to sort of say what the result is for these sorts of systems. So if you have a service distribution and a corresponding density function, it turns out that the nice way, or a fact that allows a nice analysis of these shortest job first queues, is that once a job arrives, let's say a job arrives with service time X, you can ignore all the jobs with higher service times because all those jobs are not going to interfere at all with that job that arrives, right? So I'm a job that arrives, my service time is 5. There's a job on the queue, that job has to finish. But after that point, whenever that job finishes, I'm never going to be interrupted again after that with any job that has a service time bigger than 5, because it's shortest job first. Those jobs will just stay out of my way. So it turns out that the only important quantities in determining things like the time a job is going to have to wait for a job with service times X is the total rate of inflow of work in the system. That is, so this rho value, this integral represents the total rate at which work flows into the system in total. And then the second term, rho X, is the rate of inflow of work for jobs specifically with service time less than or equal to X. And the result that comes out of queuing theory is that the expected waiting time in queue for a job with a specific service time X is given by this fairly simple formula that just depends on the service distribution, its first and second moments, and in particular on these rho and rho X values, the rate of the inflow of work into the system in total, and the rate of inflow of work for the jobs with service times less than or equal to X. And so, some of my early work in this was just saying, people in the queuing theory side haven't seemed to look at this issue of specifically machine learning models. What can we say about this sort of machine learning setting where we have this two-dimensional, this joint distribution function on predictions versus the actual sort of system. Okay. And again, the rough analysis, and I see there's sort of a typo here I should fix, is that we have the sort of same, we can run through the same sort of type of analysis. Now the actual work that's done, or the actual scheduling that's done, is based on the predictions. And so you can use the fact that once a job arrives, you can ignore jobs with higher predicted service times. You only have to worry about jobs that have a predicted service time lower than your predicted service time. And so nicely, we can think of, again, the corresponding quantity here, this rho prime of Y, is the rate of inflow of work for jobs with predicted service less than or equal to Y. And instead of just being a sort of one dimensional integral, it's now a two-dimensional integral based on this two-dimensional joint density function. But sort of the key thing that pops out going through the analysis is that you get essentially the same equation, right? Except everything is based now on the predicted times instead of on the actual times. So the expected time for a job with predicted service time y can be given by this quantity, which looks pretty much exactly the same as what we had for going back to the previous slide for the standard shortest job first setting, except that row x on the bottom has been replaced by this row prime of y, the rate of inflow of work for jobs with this predicted service time. So one of the things I suggest is like following all the price of type terminology that we like to use in computer science, is that we might call something like this the price of misprediction. That is, we can consider an algorithm that had the full and complete information without the prediction, and we can consider an algorithm that has to use predicted information. We can say, what's the cost of the price in terms of, again, just a sort of a competitive ratio between an algorithm with the information and the algorithm without it. And here, I'm not trying to say that you're necessarily using the optimal algorithm. It's not a competitive ratio necessarily against the optimal, but just against like, what would this algorithm do if it had the full and complete information versus what does it do when it has these sorts of predictions. And the point is that, at least in this case, most of the terms cancel out, and you get this sort of very, I guess, simple integral expression, or relatively nice integral expression for the case of shortest job first, telling you what this ratio will be. Just some idea of like some examples. And the idea here is to suggest that this can also be useful in, I think, practical settings, right? So here I'm showing the results from equations versus simulations. And so I'm looking at, the standard version is shortest remaining processing time. With predictions, it's shortest predicted remaining processing time. And FIFO is just first in, first out. Same with shortest job first and shortest predicted job first. Okay. And here, this is just an example with a rather simple prediction model. So the service times are themselves exponentially distributed, and we'll use a prediction for a job whose true size is X that is itself exponentially distributed with mean X. That's not necessarily supposed to correspond to any sort of actual prediction structure. It's just, kind of nice mathematically for deriving out equations, as exponential distributions are in queuing theory. And I guess the key things is that, the equations and simulations up to, small orders of noise that you expect from simulations match very well. But to me, the other main point is that, the amount that you get from a prediction, the gains that you get from a prediction are very substantial, right? It's much closer to the full information answer than it is to just saying, well, forget about it, predictions or anything entirely, I'll just use first in, first out, right? That you can get very significant gains even when you're using, not particularly good predictions. And particularly in scheduling, this seems like a really key area where you could get these sorts of gains, because the point is that in scheduling, you don't really have to have good predictions. What you really have to do is make sure you're ordering the jobs in the system correctly. So your predictions can be reasonably off as long as you're actually ordering things in the system in the right order, so that the shortest jobs come first. An example of this I like to say is that if your predictions just took the real service times and multiplied them all by 10, right, they'd be very bad predictions, but they'd still be very good at keeping the correct ordering, right? So, and I think this is a key issue in terms of trying to connect to the machine learning people to make clear that they know like this sorts of, what is important about the prediction for the problem that you're trying to solve. Here's another sort of simulation. Here, predictions are uniform over you know, a sort of discrete range that gets bigger and bigger as we increase alpha. This is for exponentially distributed service times and a more heavy-tailed Weibel distributed service times. And the key here is just that this sort of shows that in these sorts of systems that you can degrade very gracefully even as your predictions get worse and worse, which is sort of a nice feature. So for single queues, some high-level messages that it turns out preemptions is good. But again, I think the key thing is that even weak predictions can greatly improve scheduling. We just want to get the order right. And that you can do analysis under reasonable, at least from the queuing theoretic side, types of assumptions. Naturally, as people know, I'm very excited about the power of two choices. So I've been looking at this in this setting with the power of two choices. So here we imagine a large system with n queues where we think of n as, again, being large, going to infinity, the arrival rate scaling up accordingly. If you just decide jobs randomly, you'd get n parallel mn1 queues, so it would just go back to the system we were analyzing. A natural thing to do is to join the shortest queue. And the power of two choices says that, you know, for situations where keeping track of the shortest queue is too expensive, you can just pick the shortest of a small number of randomly chosen queues, and it improves over just choosing jobs randomly exponentially. So this is known in the case of multiple queues. And it turns out that if we know the service times, right, you can actually look at these systems. This was done by some other people, by Benny von Hoot and others, that say that you can actually analyze these systems for the case of looking at least loaded, where by load I mean the actual amount of service that's required on a queue. And you can do this for first in, first out queues. Okay. But this leads to some interesting open questions even without predictions. Like if you actually knew the service times, why would you be using first in, first out queuing? You'd probably be using something like shortest remaining processing time. And trying to analyze, you know, using the least loaded of your D choices plus shortest remaining processing time does not seem to be known how to analyze that. Simulations show that using both least loaded and the shortest remaining processing time can give significant gains. This is, I think, an exciting open question in queuing. We can also look at predicted service times, right? And then to me, the interesting thing here is when you're using multiple queues, you're trying to choose the best of D, how should you use these predicted service times? Because you can use them in multiple ways. You can use them to decide which queue to choose based on the load of the queue or the predicted load on the queue. You can use them to order within a queue, or you can order them for both. Okay? And you know, the question is, you know, do you really want to use this predicted information in both ways? How do things behave? Again, as a baseline, we're just going to look at this sort of exponential prediction model. And the idea is that when a job finishes, you recompute the predicted load at the queue. Right, so here's just some figures. Again, so keep in mind that when you're doing the best of power of two choices, you're already getting huge gains. So using FIFO is already like, but using FIFO but with two choices is already a huge win. But you still get even more wins by using predictions. Okay. You can still improve things even further. But one of the things we see here is that you may not want to use the predictions both for deciding what to do within a queue and in choosing a queue. That might be overusing the information. It turns out that using the shortest queue as opposed to the least loaded queue gets a little better performance. And I think this is going to be a key issue when we think of using predictions in algorithms, particularly when we're thinking of using sequences of algorithms on top of each other, that we wouldn't want, you know, our multiple use of predicted information to actually lead to bad effects because we're overusing the predictions in ways that end up hurting each other. And this, I think, is an interesting example of the possibility of that phenomenon. This is with heavy-tailed service times, one of the things we see here, and I'll explain a bit more about that in a second, is that preemptive predicted shortest job first is better than shortest predicted remaining processing time. I can discuss that, but let me keep going just so I don't go over time. Right, so one of the issues is that if you use the predicted version of remaining processing time, you can run into some pathological behavior where, if a very large job, if a job that size is 100, but you predict that its size is 1, right, that its time is going to take is 1, then its predicted remaining service time will be 0, and it will sit at the front of the queue for a long time, blocking all sorts of other jobs. Okay. So I think that's just, you have to be careful or find some variation when you want to use that sort of thing, such as using the shortest job first or other remediations. You have to be careful if that's a potentially bad behavior. The best policy can vary with the size distribution and error distribution, which corresponds a bit to the robustness ideas that Ravi was talking about for our online algorithms, that there are certainly going to be settings where you may want to pick a safer policy depending on your trust level in the predictions over what might appear to be the best policy. In the multi-queue systems or in the queuing theory considerations, you can get into some interesting variations. Like if I know the queues are using shortest remaining processing time, I might not want to go to the least loaded or the shortest queue. I just may want to go to the queue where I can get served first, right? So that would be a selfish queue choice or an altruistic queue choice where you sort of say, I'm going to go to the queue where I do the least damage to the overall time. These seem to have only small effects. All right, my last little bit of queuing, which I'll try and get through quickly. I've been looking a lot lately, and we'll soon have a paper up on the archive, I hope. I think it's mostly done, about what to do with 1 bit of advice, right? So here I'm just saying, instead of getting a guess for the service time, you can just get 1 bit, okay? And there's a motivation for this. This would correspond to threshold schemes, like the 1 bit would tell you, are you above some threshold, in which case you go to the back of the queue, or are you below some threshold, in which case you get to go to the front. Okay? And from the machine learning standpoint, like I have this idea, and I don't know if it's true, and I hope to talk about it with machine learning people, that this may be a good idea because it may just be easier to create predictions where all you're trying to do is guess if it's above or below a threshold than trying to actually get an estimate of the actual service times, that you may be able to fine tune the system for this sort of scenario. The other thing which I'll just remark on is that some of the math that comes up is kind of fun. Basal functions of the second kind I think I had heard before, but never a major G function. And this comes up in some of the integrals that pop out. But one of the main things is that even 1-bit predictions do really well, right? Even just a bit of prediction can gain a lot, right? So here I'm looking at FIFO. I'm looking at both preemptive and non-preemptive versions, again, using this sort of standard model that I've come up with, that service times are exponentially distributed and the predictions are themselves exponentially distributed. And you can see that, across a variety of loads, you do much better than first in, first out, even with 1 bit of prediction, and you do fairly close to the shortest remaining processing time. For a heavy-tailed Weibull distribution, again, you get the same sort of effect. You get huge gains, even bigger gains over FIFO. You may be slightly further away from the shortest remaining processing time, but the key is that even 1-bit predictions can do remarkably, fantastically well, which I think is promising for the practicality of these sorts of situations. You can also look at 1-bit schemes in the context of the power of 2 choices. Here I looked at an example where there are short jobs and long jobs, and you're just trying to predict if jobs are short or long. And just quickly, one of the fun things here is that in this sort of system, this last column, last row in the table corresponds to a setting, because there are a lot of short jobs and few long jobs. This setting where you're predicting short jobs incorrectly with over 60% of the time means that overall more than half your predictions are wrong, but you're still doing better than choosing the shorter queue. And that's because getting the long jobs correct is what's actually important, right? You want to make sure that long jobs go in the back. If short jobs get misclassified, it's just not as big a deal. So this is like a proof by example that you can get more than half your predictions wrong and still do better than not using predictions, as long as you get the right jobs predicted correctly. So scheduling and load balancing are natural places for these sorts of algorithms. You know, I like to use a probabilistic model. Still tons of interesting things left to explore. And in particular, this idea of like trying to tell the machine learning people, here's what I want for my predictions, right? I really want to get long jobs correct and short jobs don't worry about, you know, is the sort of feedback I think that we as algorithmists can then give back to the machine learning people. Another interesting issue is the question of fairness. When using these sorts of predictions, it would be sad to be put in the back of the line and have to wait longer for no reason other than that you were predicted poorly, but how to handle that is not clear. All right, in my last 5 to 10 minutes, let me quickly change topics and talk about learned Bloom filters. This is a way of doing better than standard Bloom filters in a data-dependent way. It's assuming that the set has some sort of structure that you can learn. So you can use machine learning to develop a sort of oracle that provides the you can think of as providing a probability that an element is a set. Okay. So the idea of learned Bloom filters is that you treat it as a classification problem. Your set is the positive elements. You pick some collection of non-elements as negative examples. You derive some sort of learning theory type structure to give you a probability estimate that your input is in the set. And then you choose a threshold. You say things above the threshold I'll just declare to be in the set, even though that might give some false positives. Below the threshold are negatives. If you just do that, there may be false positives and false negatives. So what you have to do is add a backup Bloom filter, right? So this is what a learned Bloom filter looks like. You get an input. You decide based on the learned model, should I accept it? If I don't accept it, then I'm going to do a backup check against a regular Bloom filter. And the point is that this can be smaller than a regular Bloom filter just to begin with, because this second Bloom filter, this backup Bloom filter in the bottom, can be smaller because it's only going to have to handle the elements that were negatives from your learned model. So if your learned model is good enough and small enough, you'll save size because you can use a much smaller backup Bloom filter and the learned model itself is small. All right, so that's the old work. The new work is based on this idea that, you know, if one backup Bloom filter is good, maybe multiple backup Bloom filters is better. And the idea is that instead of just having a single threshold, right, the threshold is supposed to be giving you an idea of a probability that the element is in the set, right? So we should be using different sorts of thresholds and using different sorts of backup Bloom filters to optimize, right? In order to say, well, if there's high scoring elements that we think are in the set, we don't need to spend a lot of bits on testing them in the backup. We need to spend the bits in the backup Bloom filter for the scores, the elements with scores that it's really not clear if they're in the set or not. We'd like to take them, but there are enough elements that aren't in the set that it may cause us problems, right? So you can think pictorially that it looks like this. If we think of the bottom from 0 to 1 as being our score space, ideally, if we have a good learned Bloom filter, the distribution of keys represented by f of x is going to have a bunch of high scores. Non-keys represented by g of x is going to have a bunch of low scores. And so we might want to partition, you know, it into regions and determine how many bits to assign to this backup Bloom filter based on, you know, how many keys versus non-keys we expect to see in each region. All right, so you can set that up as an optimization problem. So this assumes, you know, you're given some number of intervals k that you're going to divide it up. You're given the learned model, so we assume that you have good estimates for the various, or you can get good estimates for various regions. as to what the score distributions are for keys and not keys. And you have some sort of target false positive rate, right? So roughly you can set up an optimization problem. Capital F is going to be the distribution for keys. Capital G is the distribution for non-keys. So this first line is saying, let's minimize the space of all the total Bloom filters. Given the constraint, this first constraint says that the false positive rate over all the intervals for the non-keys should be less than the target false positive rate. And of course, the false positive rate for each region should be at most 1. All right, so if I gave you a set of thresholds and said to optimize, then you can use the KKT conditions to solve and find the optimal false positive rates if we remove the constraint that the false positive rate for each interval is less than or equal to 1. Now, often, if you solve this, you'll get that the false positive rate for each interval is less than 1, and we can deal with cases where that's not the case, and that's described in the paper. And we get some really interesting key findings, that the false positive rate for a region is proportional to the key density, inversely proportional to the non-key density, and the space saved is proportional to the KL divergence between the key distribution and non-key distribution as bucketed by these regions. Or summarizing this, the false positive rates are proportional. This F term and G term, this is the sort of fraction of things with scores in an interval, keys in an interval, versus fraction of the things that are non-keys that show up in that interval. You can come up with an expression for the total space used, and again, it depends on this information divergence between the two distributions of the score sets. And you can come up with an expression for the total safe space saved over a regular Bloom filter. All right, so that said, well, if you give me the right threshold, if you give me thresholds, I can find, the best space setting. Now the question is, well, how did you find the best thresholds to begin with? Okay. So we use the fact that the space saved is proportional to the KL divergence. So we want to find a partition that maximizes the KL divergence. And we show that we can do this at least approximately using a discretized dynamic programming. And we also have some other results, like that the space saved improves with the number of partitions, but generally a small k, a small number of partitions like 5 or 6, generally gets you almost all the way there. So here's some test data, some synthetic data with keys and non-keys given by power laws. The URL data set is like trying to determine good versus bad URLs, spammy versus non-spammy URLs, and same thing for Ember, but with portable executables. And the key thing here is, I think, to look at the bottom first. The bottom sort of says, what is the distribution of scores for keys versus non-keys? And so starting with the synthetic data set, we set up a synthetic data set that behaves like how you would want your data behave. You'd want your keys to be emphasizing very high scores, your non-keys to generally have very low scores. Okay? And in such a case, what we see is that the space used versus the false positive rate curve for our version, the PLBF, partition learn Bloom filter, is much better than, of course, standard Bloom filters, but also previous learn Bloom filter versions. And so sure enough, when we look at a data set of URLs and we look at their score distribution, and it's at least similar to the synthetic distribution, we get similar sorts of large gains in terms of space versus false positive performance. Now for the Ember data set, you can see that the key distributions are not quite so nice or not quite so divergent between keys and non-keys. So we still get gains, but they're not as significant as in the case where, our learning structure is able to divide up keys and non-keys in a better way. All right, so good, since I'm about out of time. This is the partition learn Bloom filter. There's a new archive paper up on it. Is even better than the learn Bloom filter. And I think what's nice about it is we've been able to frame this as a natural optimization problem. And what comes out is a pretty nice mathematical interpretation of the results. And we are waiting to see tons of applications for learned Bloom filters, just as there are for regular Bloom filters. And just to conclude, I think this is a great direction forward for algorithms. As an example of beyond worst case analysis, it allows us to make provable statements of the form, if you can give me something where your predictions are this good, then I can give you an algorithm that performance that will in turn be this good. And so it's a way for us to use machine learning as a black box without even necessarily needing to peek into the black box, but use it in an effective way as algorithmists to come up with provable statements that we view as valuable, but should also be valuable to the practitioners who want to use machine learning in their algorithmic work.
Okay, cool. Thanks, Michael, for an excellent talk.
Thanks, Piotr.
I think we have a couple of minutes for questions. There is a question by Temis Goulakis. Maybe I can read it. Is there a way to quantify the quality of the predictions based on the joint distribution and possibly the specific problem at hand? That is, can you talk about robustness in some sense?
So what I believe, I've been focused on sort of the more queuing theoretic point of view of I am just going to take this as a distribution. There had been some prior work that had looked at a variation where I think it's you had some sort of bound on the error model as opposed to a direct error model. My take is that you can use this as an input or as a framework to try and say, well, now if I assume some sort of appropriate bounded error model, now I have these equations and I can plug into equations and see what sort of bounds I can say coming out. It can be a bit difficult in the queuing theoretic setting because, as we've seen, there are these non-linearities, right? So I don't think it's going to be as simple a characterization, right? Primarily because of the fact that, as things get close to as you get the load close to the available service in the system, you get these nonlinear effects.
Cool. Any other quick questions? All right. So if not, let's thank all the speakers today for very very broad and clear overview of the field and future directions. So I'm just going to clap again. And I think we are out of time. So just in case, just like a few words. So we'll ask you guys to send us the slides. So hope you're okay with it. And we are going to post them on the workshop website. The workshop website has a bunch of other resources. So if there are some surveys or